Welcome to all the participants. I wholeheartedly welcome our today's guest speaker, resource person, Dr. Uday Kumar Khadke sir. Sir has also joined. Sir, can you switch on your video, please? Uday sir, Uday sir. Am I audible, sir?
Yes,
Good
sir.
evening. Good evening, sir. Namaste, sir. Namaste.
Very good evening. Very good evening to all participants here. And it's
Yes.
really good to see you on the screen after a long time, Galgali sir.
Yes, sir.
Very
Thank
happy
you.
to
Thank
see
you so much, sir. Thank you. It's my pleasure and privilege also. And to all the participants, I will be very happy to introduce to all of you today's resource person, Dr. Khadke Uday Kumar sir. And here is his brief biodata. I am reading for the information. Dr. Khadke Uday Kumar sir is a professor of physics, Dean, Faculty of Pure Science, in Faculty of Pure Science and Director ICT at Vijayanagara Sri Krishna Devaraya University, Ballari, and has also served as a special officer at Vishwesvaraya Technological University, Belgavi. He earned his PhD in physics from Gulbarga University in the year 2005, following an MPhil in the year 1999 and an MSc in the year 1997 from the same institution. With extensive academic and research experience, he has held various positions including Head of the Department at Presidency University Bengaluru, BKIT Bhalki, Jain College of Engineering Belgavi, and KLS Gopte Institute of Technology Belgavi before joining VSK University. Dr. Uday Kumar sir's research focuses on ion beam modification of materials, ferroelectrics, and radiation physics. He has been a visiting fellow at JNCSR Bengaluru, a senior research fellow at CSIR New Delhi, and a project fellow under UGC NSC project. As a recognized scholar, he is a life member of prestigious scientific societies, including the International Academy of Physical Sciences, Indian Society of Radiation Physics, Ion Beam Society, Material Research Society of India, Indian Association of Physics Teachers, and the Indian Association of Crystal Growth. As a principal investigator, he has led major research projects such as ion beam induced ionic conduction of PVDF based separator for energy storage devices, funded by Inter-University Accelerator Center, and development of energy spectrometer for the measurement of energy radiation concentration, supported by Vision Group of Science and Technology, that is VGST, and electromagnetic interference shielding applications of conducting polymer nanocomposites, supported by VTU Belgavi. His publication record includes 55 journal articles, 4 books, 9 conference proceedings. In addition to his research contribution, he has presented his work at national and international platforms, including ICTP Tristi, Italy, and Science Center, Singapore. With these brief words, I now present before you and wholeheartedly welcome today's resource person, Dr. Uday Kumar Khadke sir. Sir, we are really honored by your presence, and I request your good self to go ahead with the presentations. So thank you so much.
Thank you very much, Professor Galgali sir. In fact, talking to you people is like talking to our own family members, because I have spent a quite good time with engineering colleges.
After a very, very long time, sir.
Yeah, almost 14 years I was with engineering colleges.
Yes,
So
sir.
still I feel all faculty members or those who are joining as a physics faculty in engineering colleges, they are all close to my heart only.
Yes,
So thank you for your kind introduction to the participants. I can see that the number of participants are slowly increasing. It is almost 23 participants are there. I believe that most of the people are from a physics background only. Probably they will be either doing the research activity for PhD thesis, or probably they are faculty members also for this FDP program. In fact, before starting, I really thank the organizers as well as particularly the Professor Galgali sir for giving an opportunity to share some of my experimental results with the esteemed people joined to this session. So probably I will be able to share the PPT. Shall I share the PPT now?
Yes, sir, you can share, sir. Yes, sir, you can.
Where to share? Where is the share? It is here. Okay, sharing. I will do it complete my window.
Yes.
So that whatever changes I'm doing it, it will be visible to all people.
Yes.
Okay, it got shared.
I think there will be some time delay. It will appear, sir.
I think it has shared already.
Yes, yes, yes. Now, I think has to be some another processor. Instead of sharing windows, if there is any other.
Okay, share. Select entire screen.
Entire screen, sir. Go ahead with that. Entire screen can work.
Now it's visible.
No, sir. It is at the background, I guess. I don't know, but we are seeing the present window itself.
Present window. Now I will be sharing my PPT.
And yes, sir. It is. Go ahead, sir. Go ahead.
Okay. Now this
It is. Yes, sir. Yes.
Visible.
Yes, sir. It is visible, sir.
Okay.
Yes, sir. It is visible.
Right. Now I will be talking on ion beam technology for micro and nano patterning and its application. In fact, Professor Galgali has insisted me to talk on nano patterning, but whatever the experimental result we achieved it by ion beam technology are more or less in the range of micrometer. But having said this one, I will just justify saying that why we got a micro patterning and its application that I will be talking up in the session. And some of the results which has been obtained by one of my friends at Central University Hyderabad with his permission, I am also sharing 1 or 2 slides how the nano patterning will be created by ion beam technology, what are the mechanism, all those things. Well, I am at presently at Vijayanagara Sri Krishna Devaraya University, Ballari. It is closer to Hampi University. Started in the name of Vijayanagara Sri Krishna Devaraya. Our university, in fact, it has started just 2010, in the year 2010, and we are just for 15 years old baby. And in fact, we have quite good number of faculty members, and in physics department we have 4 faculty members are considered to be 4 pillars of the department, and all 4 peoples are doing extremely good in their respective field. So vision of the university started with Sanskrit slogan called Dhiyo Yonaha Prachodayat, in the sense envision the power of mind. So harnessing the power of mind and cultivating the ethical culture among the students. That is what the motto of our university. And at the same time, not only instilling the ethics among the students and how the research activity has to be strengthened in the department, that also we will be doing it. Well, my field actually it is based on the utilization of Pelletron accelerator facility. So before starting the Pelletron accelerator facility, just let me tell you that in India, there are only 2 Pelletron accelerator facilities. One is located at Mumbai, Tata Institute of Fundamental Research, that is TIFR, and another Pelletron Accelerator is located at New Delhi. So the Pelletron Accelerator facility, which is located at Delhi, is open for all researchers throughout the country. Anybody who wanted to do the research activity with the state-of-art facility, they can write the proposal. And if the proposal is through, then you will be able to use that facility. And when you're using that facility, no a single paisa has to be paid from your pocket. Entire financial support will be given by that organization. Plus, you will get very good hospitality also, and you will be able to do very high quality experimental result. With this note, let me start my presentation. And my presentation is restricted to these many points. I will be just introducing what exactly the ion beam technology is in order to modify the material's property, and what is the motivation behind using this ion beam modification technique. So I will be touching upon what are the fundamentals of ion beam techniques, in the sense how this ion beam or charged particles will be interacting with the material atoms of the material, and how the properties of the materials are going to change it. So one of the important mechanism where the material is changing its property is by creating a pattern either on the surface or in depth of the material. Then experimental facility, what is available at Inter-University Accelerator Center, where it is located, this center is located at New Delhi, where a Pelletron Accelerator facility is there. How it can be utilized, a little bit about that I will be just explaining it. And using that facility, in fact, we did two important projects at present. One is modifying the ferroelectric polymer using different types of charge particles, and we will be seeing two important applications out of it. One is electromagnetic interference shielding effectiveness, and another one is how this PVDF can be used as a good candidate as a separator in rechargeable battery. So these are the points that I thought of just explaining to you people. So probably I have been given total 1 hour 30 minutes. I will stick to my time so that I can complete it within that 1 hour 30 minutes. Well, now the first question rises, why the modification of the material is required? Friends, you might be knowing it, that in the earlier days, when you ask the question to the students that how the material are classified, or how the materials are classified based on the conductivity. So usually student used to write down that the material are classified into three categories based on how well it conducts. One is the material which shows good amount of conductivity. No doubt it is considered to be good conductor. Metals are considered to be good conductor. Whereas the material which does not show any amount of conductivity, I am talking about electrical conductivity, because there are different types of conductivity will be there. You can consider as a thermal conductivity, you can consider as an optical conductivity, or you can consider as a mechanical property is also kind of a conductivity. So based on the electrical property, one can consider that the material which shows good amount of conductivity are considered to be conductor. The material which does not show any amount of conductivity are considered to be insulator. The material which shows the conductivity between these two materials are considered to be semiconducting material, is a well-known definition. But if the same answer is written nowadays by students, probably the teacher will not give complete marks. Reason is that the main important point has to be mentioned that at a given temperature, when you are mentioning at a given temperature or at a given circumstances, certain material shows good amount of conductivity, certain material shows good no conductivity, and certain material shows conductivity between these two. In the sense, the surrounding parameter is also playing an important role where the properties of the material is going to change it. Now you take down the glass material. Glass material at a room temperature, one can expect that it is completely insulating. But there are many glasses which has come into the market due to the potential researchers that there are conducting glasses also, which means that the conducting property of the glasses has been changed. So at the same time, when you are having good conductor, like take down an example of copper, it is very good conductor at a room temperature. But thing is that the moment when you reduce the temperature closer to 0 Kelvin or around 4 Kelvin, you will not be able to see the superconducting phenomena, right? So that is what, though we are considering one particular conditions, but the property may changes according to their circumstances only. So with this mind, now we will be asking why one particular material, is it possible to make it insulating material? Is it possible to make the same material as a semiconducting material? Is it possible to make same material as a good conductor? The answer is yes. You need to modify with the different techniques. So modification, there are n number of ways where you can modify the materials. One is considered to be making a composite out of it, right? The composite of it, we can make it where the strength of the material can be prepared. So another thing is that in order to make it good optical property of the material, you can just mix some other foreign materials and make it either transparent material or opaque material. So optical property will changes. At the same time, now you can just dope some foreign materials, appropriate foreign materials. You will be able to see that there is definitely a change in the property of the material. It is something like doing a material science research only. Doing material science research is nothing but simply doing a cooking at the home only. So you might have seen that when a person is cooking in the kitchen, so different ingredients will be used so that the taste will be different. So one thing is understood that when you are having different gradients in the food, so obviously the taste will be different. And that is the reason sometimes in earlier days, we used to say that when a mother is prepared a food or a grandmother is prepared a food, grandmother is prepared a food, the taste will be different. So taste is different in the sense probably there is a modification in the food, and that is the reason the taste is going to be changed. So now why the material property has to be changed is a big important question. Now, for example, in medical implants, you need a biocompatible materials, in the sense whatever the foreign materials you are putting into your body, usually body will not accept any foreign materials. But if that foreign material is compatible with the mechanism of the body, then there is 100% surety that these foreign materials can accommodate into the material. And at the same time, when you're modified, this biocompatible material is implanted into the body, the durability must also be very, very large. So obviously, the material modification has to be done. Coming to this satellites, now you might have heard about SBS-3, that is satellite-based surveillance 3. The program, in fact, it has to be done completed by 2030. But due to the emergency, due to the urgency, central government has imposed a condition that this program has to be completed by 2026 only. In that, nearly 20 satellites will be prepared by ISRO scientists, and nearly 22 satellites, 32 satellites will be fabricated by some other agency, which will be supported by Elon Musk or all those things. Now, probably people might have heard about this one. 52 satellites will be put up into geostationary or geostationary. Okay. Now, the purpose of putting the satellites into geostationary, you need a lot of fuel to lift that satellites from the Earth to that orbits. So when the material weight is more amount of fuel is required. That is the reason you need to modify the materials that you're using into the satellite so that it becomes completely lightweight and a less amount of fuel can be taken so that it can be put up into the required orbit, and you will be able to use that satellites in order to understand the climate change, in order to understand uh, what you call the movements of the terrorist, in order to understand how the border security is made, and you will be using high resolution cameras in the satellite so that from the satellites one can see what is the movement on the earth is taking place. Is there any illegality is going on? So entire movement can be captured very well using the high resolution camera, which is put up into the satellites, 52 satellites. And at the same time, the AI concept is also used in order to communicate between satellite to satellite, and you will be receiving the information to the earth so that entire country, it's a plan to have entire country should be completely secured from unwanted aspects. So you need lightweight, so that modification is required. Well, modification in the sense, how kind of modification is to be done? So one important aspect is, suppose if you are having a material in the form of bulk, so you reduce the material, that bulk material, into nano size. You reduce the bulk material into nano size. So one of the best modification way is reducing the dimension of the material. So reducing the dimension of the material in the sense, probably you might be knowing it, or you will be, you already heard it. There are different techniques in order to reduce the size of the material. One is considered to be top-down approach or bottom-up approach. Using that two techniques, you will be reducing the size of the material. And believe it, when you reduce the size of the material, the property are going to be changed drastically. One of the beautiful example, let me tell you, by considering an example which has been considered as pizza paradise. Pizza paradise. One story, let me narrate it here. A king visited to a hotel and asked the waiter to get one big size pizza. Then waiter has asked what size pizza you require. Simply said that somewhere else around 12 centimeter pizza you bring it. That is a conventional. I'm just taking a number. Okay, 12 centimeter pizza you get it. So waiter went into the kitchen and saw that there is no pizza available of that size. He came back to that king and he asked, "Sir, I don't have at present that 12 centimeter pizza has been exhausted. If you want, I can give two 6 centimeter pizzas at the same rate." Then, of course, the king, after all, king only. So he said, of course, getting 12 centimeter pizza one is equal to getting two 6 centimeter pizza. So he said that go and get it. Okay, so he ate, but he could not be satisfied as he expect to be satisfied with 12 centimeter pizza. Now here, physics and mathematics involves. So what will be the size, what will be the volume when you calculate with a 12 centimeter pizza, and what will be the total volume when you calculate the two 6 centimeter pizza? Surprisingly, if you do the calculation, it says that the 12 centimeter pizza will be equivalent to 8 quantity of 6 centimeter pizza. So instead of getting one 12 centimeter pizza, he must be able to get 8 6 centimeter pizza. Then only it will be balanced. So how he realized it? The moment when he eat that 6 centimeter pizza, he was not satisfied. He was thinking something that he could not get the satisfaction. The reason is that as you reduce the size of the material, the surface area with respect to volume increases. The surface area with respect to volume increases, which means that as you reduce, more stuff you will not be get in the pizza. In the same way, suppose if you take down, instead of taking this bigger size, a few centimeter pizza, and make it that pizza as a nano pizza. So nano pizza, below it, you will not be able to get any kind of stuff because the surface of that pizza will be completely coated by the atom, and inner part you will not be able to reach it at any moment. So from which side you try to eat that nano pizza, you will not be entering into inside it. So which means that the taste of the food, which changes drastically because of change in the sample dimension or the sample size. So this is what the information I thought of just giving it, how the property of the taste is going to change it from macro size to micro size. Well, that is one example where you will be using nano patterning or nano dimensions in order to see the changes in the properties of the material. Now, let us come to the conventional method, how in the earlier days people used to modify the materials. Now, suppose if you want for civil engineering people, if they wanted a very what you call strengthened material, so the pure material they cannot take it. For example, steel only they cannot take down in the pure form. The pure form always it will be in the soft mode. It will be softened materials only. For example, if you take down a steel material, if you mix this iron material with certain carbon material, obviously the strength of the material is going to be changed with respect to compared to the pure iron what it gives is. At the same time, suppose if you take down a bronze, which is a mixture of copper and tin, it becomes very, very harder than the copper one. Just mixture of small amount of tin, you will be able to get this bronze material very, very strong in the strength. So this is a mechanical property where you will be able to change it just by mixing certain amount of foreign materials into the material. Another way, assume that you don't want to mix anything, then you need to play with the temperature only. What is that temperature? You can make two different type of effects of the temperature. You heat the material at elevated temperature, no doubt the material get melted up, but the moment when it get melted up, so cooling can be achieved by two different mechanisms. One is considered to be fast cooling. The moment when you make it fast cooling, suddenly the material will be of softened type of material it will take place. Oh, sorry, hardened type of materials it will take place. Sudden cooling, that is what we call a mechanism called quenching. Quenching process makes a soft material into hard material, whereas after heating it to the elevated temperature and allowing it to cool by its own without any external forces, by room temperature, just by leaving it to the room temperature, it comes to room temperature by its own, but it will take more time. That process, in fact, we call it as an annealing process. And in the process of annealing, you will see that the material will be more softened. What material? Same kind of material you get as a hardened material the moment when it is quenching. So another one is considered to be surface treatment. Surface treatment in the sense you will be modifying surface from bombarding either light or by what you call by putting a hammer on it, by putting a layer on it, you will be able to treat the surface where just by putting the surface treatment, but just by making the surface treatment, you will be able to get different properties of the material. Well, these are the conventional methods. Now, the moment when the technology has increased, the technology has upgraded day by day. So people thought that the property, particularly the electrical, magnetical, or physical properties of the material can be changed by dopant. So that is what we consider in a semiconducting material. Suppose if you take down pure semiconducting material, in fact, the pure semiconducting material will be having a very limited applications because it has limited properties only. But the moment the same pure semiconducting material, if you dope it with some other external dopant, you will be getting an extrinsic semiconducting material where you will be able to get two different type of extrinsic semiconducting material depending on dopant. If you have a base material which is a tetravalent, and if you dope it with a trivalent, obviously you will be able to get p-type semiconducting material, or if you dope it with pentavalent, you will be able to get what do you call it, the n-type semiconducting material. So n-type semiconducting material and p-type semiconducting material, in fact, we call it as extrinsic semiconducting material. And these semiconducting material, which is considered to be a treated semiconducting material, and if you join, you will be able to get the devices. And devices makes very, very important, revolutionary in our life. Whatever the electronic gadgets, a kind of computer, we are seeing it in our hand, a mobile is considered to be a replacement of the mobile computers only. That mobile is also considered to be a computer. So miniaturization is taking place the moment when the revolutionary in the semiconducting material has been taken place. About the semiconducting material. So first part I have explained about the conductor. Second part I have explained about the semiconductor. Now insulating material. The glasses or the polymer materials are considered to be insulating materials in nature actually, but there are certain natural conducting polymers also, like what do you call pani, and all those things are considered to be what do you call conducting polymers. But most of the polymers are considered to be insulating materials only. Now these polymer properties can be changed by insertion of nanoparticles in it. Friends, let me just make it clear that you don't have any polymers which are considered to be nanopolymers. Nanopolymers is not at all possible because the polymers itself is made up of molecules, and molecular structure is not a nanostructure. So polymer which is made up of the molecules are considered to be a molecular structure, but you can include nanoparticles in it, in the matrix of that polymer, and then there is a possibility that you will be able to get the polymer nanocomposite, which has created a lot of interest among the researchers, and they are doing a lot of activities, a lot of research attraction has been done so that they are playing with that one. Okay, so these are the three important properties, how the modification in the properties can be done. So I can consider these are all conventional method, and doing doping it, mixing it, or making a composite, all of it, there is always a possibility of having certain impurities in it, and that impurities will be having an adverse effect. Suppose for a time being, if you think that you are doing, you are modifying the materials with a technique, with a novel technique where you will not be able, you will not be putting any kind of foreign materials in it. So such type of a technique really exists, but no doubt it has slightly expensive. But in order to get quality work, people, researchers will not bother about the expenses. Well, now what is that technique? Let me tell you, that technique is nothing but ion beam technique. So how that ion beam technique, technique, or how the modification of the material can be achieved by ion beam. So the question rises, why the ion beam? Nowadays, believe me, the ion beams are becoming favorable to almost all fields. In the sense, it is interested in engineering, you can modify the materials. Engineers needs the modified materials. Material scientists, they are just a cook in the lab, similar to the cook that housewives or mothers does it in the kitchen room. So there is no difference between these two cookers. Only thing is that the lab cookers will be modifying the materials so that they can tune the properties according to their requirement. Now, what is the use of physics then? Of course, whenever there is a change in the material property, which is useful for the engineers or which are useful for the material scientists, why that changes, what made the changes can be understood are fundamental things by a physicist only. How this interaction between the atoms and atoms, between ions and atoms, or between ions and ions will take place. So this reveals an important information to the physicist, where the physicist helps us to find out the important mechanism which changes the properties of the material. And based on that mechanism, people started working on different phenomena, and they will understand that if this mechanism is incorporated, obviously this kind of modification will take place. So in that way, the physicist is required in order to understand the concept between the interaction between ion and the particle. When ion beam modification is the most important, one entity is where you will be modifying the materials. Another entity is also interesting when you are using the ion beam technology. As you are using X-ray diffraction, why we are using X-ray diffraction? X-ray diffraction, in fact, we use it in order to know the structure of the material, know where the atoms are sitting, what is the orientation of the planes, what is the orientation of the atoms present inside the medium, which means that you're analyzing the crystal structure, you're analyzing the amorphous structure of the particular material, where you will be using XRD, Raman spectra, optical phenomena, optical instrumentation, you will be using it. Apart from that one, if you want to know the exact crystal structure, the structure of the material, one of the best method is considered to be ion beam analysis. So these are the important techniques that I just thought of mentioning you. What is the use of ion beam processing? Well, this is the conventional technique that we are seeing it. You have host material, and the host material to the host material, you are just putting the ions or the electrons from the outer side, and you see that how systematically these ions are going and sitting at the interstitial part. In the sense, suppose if the material you are having it, large number of atoms will be sitting on the lattice points. Now this ion beam interaction, specific types of ion you are putting it inside, but what they are doing it, they are sometimes going and sitting into the interstitial, or just replacing the lattice points, just replacing the atoms and going and sitting is the ion beam. So in this process, suppose if you are having big size N-type semiconducting material, and ion beam is made up of a P-type semiconducting material, that P-type ions, you can put it into wherever you want in the interstitial part, and you will be able to get within no time the transistor type of devices. So this is what the beauty of using the ion beam. Well, these are the conventional method. You have a carbon tube, what you call multi-wall carbon nanotube, and again the property of the multi-wall carbon nanotube can be changed just by bombarding the ions on it. So usually when you are using very high energy of ion beam, there is always a possibility that this carbon structure will be completely broken. It becomes completely amorphous and the property of the material will changes. But at the same time, if you are using low energy ion beam, only the ions going and sitting on the surface of the carbon nanotube, the properties of the material is going to be drastically changing. Well, this is what the example I am thinking of giving it. So you have a silicon wafer which is made up of a pure semiconducting material, and the other type of semiconducting, you are just injecting it from the upper side. It goes and sits in a systematic way at particular level, and this will give completely a different form of devices. You may be able to get diodes, you may be able to get transistor, you will be able to get field emission transmission transistor, or you may be, if you are making use of the metals, then you will be able to get metal oxide semiconducting material also. MOSFET also you will be able to get. So there is a possibility that using ion beam technology you can prepare the devices also. But that is not our intention, is because it becomes very expensive technique in order to make these devices. No doubt the devices will work properly, but at the same time the cost involved will be more. But essentially our intention is to modify the material using ion beam technology. Modification has to be revealed. What kind of modification will be taken place the moment when the energy of the ions changes, when the type of the ion changes, when the dose rate of the ions will changes. Okay, so all these phenomena are essentially useful in order to create a favorable defects, in order to change the property of the material from crystallization to amorphization, or from amorphization to crystallization. As well as nanostructuring is possible from ion beam technology. You have a bulk material and you will be cutting into pieces, and you will be able to see the nanostructure will be created, and that type of material will be created on the surface. Phase transition, just by putting some foreign materials into interstitial part of the atoms or unit cell, you can see that the phase transition will take place at different temperatures. So for or at room temperature also, you will be able to see there is a change in the crystal structure, though it is in the solid state. Properties, obviously the electrical property, magnetical property, optical property, mechanical property, all said different types of properties using a physical property can be understood just by modulating the band gap, modulating the conductivity, modulating its what do you call transmittance. All those things can be done. Okay, so these are the property. That is the reason one can think of using ion beam technology. Well, ion beam technology in the sense as a part of physics, what we can understand. Well, now depending on the energy and the type of the ions, probably let me take down a very basic example here. You might be knowing that knowing the nuclear radiation, that is alpha particle, beta particle, and gamma particle. Now you know that probably I can take small what do you call a gap in order to understand whether all the audience are attentive or not. Otherwise, it becomes completely one-way show. I'm just explaining it, whether the people are receiving it at the other end or not. Let me just
Sir,
check down.
receiving, sir. Receiving, sir.
Good.
Yes, sir. There are 52 participants, sir.
Thank you.
Going on, sir. Please, sir.
Okay.
Yes.
So now, now you know that when you are having a gamma particle penetration power is very, very high. It can penetrate any thick material. It's a property of the material. Now, the moment when you take down beta particles to a certain extent, it can also penetrate into the material, but the depth of penetration compared to the gamma will be very, very less. It is considered to be a charged particle. So because of the charge particle, there will be a hindrance in the material, and suddenly the beta particles will be stopped in the material. The range will not be that maximum as compared to the gamma particle. But if you take the alpha particle, it is considered to be heaviest particle compared to beta particle. Sometimes beta particles are considered to be electrons also, is it not? Now, whereas alpha particles are considered to be doubly ionized helium atom. Doubly ionized helium atom is nothing but is ion only. Alpha particles are positive charge particle. But positive charge particle, if you put it that if the alpha particles are coming outside from the radioactive source, it can move, it can travel with a distance of around 4 to 5 centimeter only. Now, if the thickness of the material is very, very large, only on the surface it hits. So no chances of penetrating inner side. So which means that why we are telling this one, the penetration of a charge particle is essentially depends on what type of charge particles you will be taking it. In the same way, as you consider as alpha particles are nothing but a doubly ionized helium atom. So you can consider that you have different types of atoms whose electron affinity is more, and you remove those electrons, outermost electron, no longer that atom will remain as an atom, it becomes an ion. So depending on the energy, if the energy is very, very less, so there is a possibility that these ions can penetrate into the material and get deposited inner side. But before penetrating inner side, when it is hitting to the surface, there is always a possibility that some of the ions get reflected back, or the atoms which are sitting on the surface getting getting sputtered on the upper side. So sputtering is nothing but erosion that you are creating on the surface. So erosion will be created with very fine structure, which is of the order of around few nanometers only. That is nothing but a nano patterning. So sputtering of the ions from the surface of the thin films. Due to sputtering, you will be able to create a nano patterning on the surface. But thing is that you need a specific type of material, usually hard material. When you are having hard material, either it is considered to be semiconducting material or a conducting material considered to be hard material. And when you are putting energetic ions on the surface, the ions on the surface will get sputtered and erosion will take place. And that erosion will be very, very fine, having a dimension of erosed area will be of the order of few nanometers. Next is scattering of ion beams, which is hitting to the metal surface, and after hitting, the ions which are hitting, that ions will be either getting reflected back, or it will be simply transmitting, or reflection will be happening in all the directions. Now, these scattered ion beams, if you collect it at particular angle, below it, the information about what type of material is there, that can be understood very well. So scattering analysis is most important. Damages, sometimes damages, it is considered to be a crude word for a normal person. For a scientist people, damage is always favorable. So certain damages will be helpful for medical people. Certain damages are very, very helpful for the space satellites. Certain damages are very, very helpful for tuning the properties of the material. So these are the important mechanism that you will be able to cherish it the moment when you're using ion beam. Now, how you are getting these one is most important. Now, when huge amount of ions, positive ions hitting to the surface is considered to be a collective number of ions hitting to the surface. So sometimes this collective number of ions which are hitting to the surface are considered to be swift heavy ion. So when the swift heavy ion hits to the material, as I mentioned in a normal word, the erosion will take place, or the ions will get reflected back, or the damage will be created. The ions will go sit into the interstitial, or the ion will replace the atoms, or the ions will kick off the electrons of the atom. Such things will happen inside the medium. So based on that one, we can quantify what kind of mechanisms are taking place, which is more interested to the physics people. Now, when swift heavy ions hit through the material, this heavy ion loses its energy by a mechanism called electronic excitation. Let me put it in very simple mechanism. Assume that you have one atom. And obviously, atom consists of large number of electrons which are revolving continuously on the nucleus. When you are having ion with a larger kinetic energy, it has a chances that it can penetrate directly inside the atom. Maybe there is a chances that it can collide with the electron. Electron will come outside, and electron will come outside. When it is coming outside, conservation law should obey there. Whatever the energy of this ejected electron has taken place, that much amount of energy will be lost by the ion which is penetrating. So this entire mechanism, in fact, we call it as the energy of the ion loses due to electronic excitation, or electronic ionization will also take place. Electronic excitation or ionization. Ionization is simply
మార్కు ముందు ఏ అక్షరమును జోడిస్తే ఒక కొత్త పదము ఏర్పడుతుంది.
Yeah, there is some sound coming
Sir,
from
I will mute them.
Okay, fine.
Participant, please.
Well, electronic excitation. If the energy of the ion is very less, then obviously one can think of the ion will not go inside the atom, but as a whole, it has a tendency that it can shift the atoms. So atom, most of the mass lies into the nucleus. And that is the reason in scientific community, this kind of mechanism, rather than calling as an atomic loss, one can call it as a nuclear energy loss. So which means that entire atom with the nucleus is getting shifted up. So it is something like you have a stone and you are throwing that stone on the glass window. If the energy of that stone is very, very less, then there is always a possibility that entire glass may break. Now replace that stone by a bullet and fire that bullet by some gun. So what kind of damages you can see it on the glass slide? Any participant person can tell that one? If I am firing the bullet on the glass window, what will happen to the glass? Entire glass will break, or it creates one small hole equivalent to the dimension of that bullet. What will happen?
Mostly it creates hole, but depends on the force it comes.
Exactly correct. Force in the sense is nothing but kinetic energy. So same thing will happen with ion here. Now, when you are having a larger kinetic energy of the ion, it will knock the electron, leading to excitation or the ionization. But if the energy of the ion is very, very less, so obviously it pushes the atom. So that energy loss is considered to be nuclear energy loss. So at very low energy level, nuclear energy loss. In the next slide, I will be showing that one. Now mixing with these ions in the material, which creates completely different phases, that is also possible. Inertial ionization, where you will be able to see a kind of X-ray kind of rays will be generated because of transition of these electrons from the higher energy level to lower energy level, which has gone upper side due to hitting the ions. Well, these all mechanisms are very, very useful in order to understand the properties of the material, in order to modulate or in order to change the property of the material, that is material engineering, in order to understand, see, whatever the ions we are taking it, so similar kind of ions will be there in the cosmic rays, in the above the ionosphere cosmic rays. Now you are sending the satellites into the above the atmosphere, above the ionosphere layer, where you will be having a lot of cosmic rays, and in the cosmic rays you will be having these high energetic ions. And when you are sending the satellite, obviously it is put up of large number of electronic components. Now, when it is having large number of electronic components, obviously those electronic components should sustain with the cosmic rays. So tolerance has to be checked. So to check the tolerance, you have radiation tolerance test. ISRO people are more interested in this kind of activities. So they take the devices which are fabricated into the satellites. Before putting it into the satellites, they do the radiation tolerance test. Atomic, nuclear, and particle physics. In order to understand the nuclear physics, in order to understand the atomic physics, or in order to understand the particle physics, what is there in the nucleus, what is there beyond the beyond the elementary particles, in closer to the elementary particles, how many elementary particles are there? All those things can be revealed by ion beam technology. Hope you all understood about the importance of ion beam. Well, what happens when an energetic ion hits a material? Obviously, it loses the energy. Who will take this energy? As I mentioned that the moment when the external ion, when it is hitting to the material or matter, obviously it loses the energy. Now it loses the energy in the sense, being a physics person should account who has taken that energy. Who else has taken the energy? Either it will be taken by atomic nuclear whole atom, or it will be taken as electron. Who will decide what share of the energy has to be taken? Obviously, the cross-section area, which is done by the ion when it is hitting to the material. If more the cross-section, more the energy will be transferred. Well, atomic displacement will take place, direct damages. When atoms are displaced, direct damage will take place, or electronic excitation will take place, as I mentioned in the earlier slide. So this is the slide which tells us what kind of mechanism will be taking place. Now, believe it, so this larger hyperbolic, what you are seeing it, gives rise to electronic energy loss, electronic stopping, in the sense the ions are getting stopped due to electronic energy loss. And this energy loss will be more dominant when the kinetic energy of the ion is more. So that is what we have given it, electronic excitation or ionization energy, which is considered to be inelastic collision. So solid ion solid interaction will be explained based on this one. Suppose if the energy is very, very small in this region. So in this region, what will happen? Atomic displacement will take place, where these atomic displacements are considered to be just elastic collision. So this elastic collision or inelastic collision are the two important mechanisms where the ions, when it is hitting to the material, are losing its kinetic, losing its energy, can be understood based on this one. Other component, now you see the beauty of this one. Now you have this particular sample and the ion is coming from the upper side. So what will happen? The moment when it hits to the surface, some of the ions get scattered. So this scattering ions gets the information about the surface material. Similar to the X-ray. X-ray will be having a limitation because of its wavelength value. But this ion will be having a larger wavelength value. So more precisely, it tells about what type of atoms or what types of unit cells are arranged in the surface of the material. Well, or else, if the energy is more, it can go inner side. When it is going inner side, as I mentioned, that electronic energy loss takes place where excitation, electron excitation or ionization will take place. So this black color is considered to be electron which are knocked. So now these electrons may interact with other electrons. Secondary electrons will be created called as delta electrons. So this kind of mechanism will be taking place inside the material. So this entire mechanism, in fact, we call it as Coulombic explosion. So Coulombic explosion model tells us how the ions, after penetrating inner depth, apart from the surface, what kind of energy, what kind of modification inside the material will changes. And that modification, in fact, we call it as Coulombic explosion. Well, other mechanism, as I mentioned, that you will be having a delta electrons also. A delta electrons, most of the times these delta electrons are considered to be secondary electrons. This secondary electrons moving in its path has large number of collision with the lattice points and loses its kinetic energy. The moment when these larger kinetic energy electrons, secondary electrons, when it is moving in the interstitial path, having the chances of hitting to the lattice points, and the lattice receives the energy. After receiving the energy, you must be able to account where this energy is going on. So you will be able to see that the material starts getting heated up. And that model, in fact, we call it as thermal spike model. It is given here, thermal spike model. Okay, thermal spike model. The color of the line indicates that how the temperature of the the material is going to change in the track of the ion. The moment when it hits upper surface, the temperature goes of the order of around 2000 Kelvin. As it goes inner side, the kinetic energy of this ion will be reduced because it has loses its energy to the electrons or the ions or the atoms to the lattice. So it comes to the halt, and you will be able to see that it reduces the temperature closer to 300 Kelvin. It comes to the room temperature. So this side, the temperature will be high. This side, at the extreme, at the exit entry, the temperature will be less. So this can be harnessed in order to patterning the material, in order to change the property, change the structure of the material. Another important mechanism, in fact, it is high school level mechanism. When a charge particle is traveling in a straight line perpendicular to the motion of that charge particle, it produces electric and magnetic field. Can we harness this electric and magnetic field in order to change the property of the material? For example, if you take a ferroelectric material which is made up of large number of domains inside it, and domains are able to rotate it the moment when the electric field is applied. Now, in order to apply the electric field, you need an electrode, and then you can apply the electric field. So electrode has to be applied, which is considered to be a kind of external damage to the material. Now, if I send this ion inside with a larger kinetic energy perpendicular to the motion of this charge particle, it will create electric field and magnetic field. Now, can we think of this electric field strength? If it is very large, can it rotate the domains? Yes. And this magnetic field can rotate the dipole moment, magnetic dipole moment. Yes. So which means that you will be able to switch on, switch off the domains, either atomic domains, dipole moments, or you can change, rotate the magnetic domains. So magnetic domains are essential, useful in order to rapidly change and give the information which is used in the computer science, whereas domains orientation of the domains also can be used in order to store large amount of information, and later it can be retraced, so which can be used as a random access memory. Okay, so these are the three important mechanisms. So an ion loses energy by Coulombic explosion, loses by electric field it generates perpendicular to that one. It loses due to secondary electrons create lot of temperature. So it creates temperature, but these temperature are localized temperature. It will not be created bulk temperature. Localized temperature will be created. Localized electric field will be created. Localized damage of the material will be created. And these are purposely putting atoms or ions inside. When these ions are moving inside, no chances of having any external material getting deposited on it, like oxygen also. All these experiment, in fact, it has to be done into vacuum only. So you will not be able to get any kind of oxygen deposited on the surface. Well, let me just skip this one in order to explain who has taken the energy. So the same thing is there. Now this diagram, one should say that what is happening. One, you are having one bigger size atom of the material, and the other side you are having Z1 plus is considered to be ion plus it is. Now I am just pushing this Z1 plus towards Z2 plus. What is happening? You see it. Well, it has gone and it has come back. So when it has come back, it has bring a lot of information. And this is similar to the experiment which has been performed by Rutherford. And then he said that, yes, there is some positive charge located exactly at the center of the atom. And that is the reason this charge particle is exactly bouncing back in the same direction. Is a well-known experimental things. Oh, these are all kinematics, how to understand at what distance this ion will reach us to the closer to the ion or closer to the material. All those things can be understood based on the mathematical equation. Well, these are the energy losses. As I mentioned, the stopping power is due to electronic and nuclear. Electronic energy loss will be denoted by SE. Nuclear energy loss will be denoted SN. And these are considered to be stopping power, which has denoted by dE by dx. In the sense, rate of change of energy when it is passing through a thickness of dx is called as stopping power. Stopping power is considered to be stopping power is a material property. Stopping power is a material property, whereas energy loss is the ionic property. So you have two different properties. One is ionic property, use huge amount of information about the material. Another one is material thickness, where you will be able to modify it with very minimal deposition of the material or just by irradiation. There are two mechanisms when you are bombarding the ions on the surface. One is when the ion hits the surface, one surface, and come back from the other surface, creating a lot of defects inside the medium, are called as irradiation. Ion beam irradiation. Another mechanism is called as when the ions are hitting to the one surface, getting inner side, and then it loses its energy and getting deposited inner side. Friends, believe it, when you are implanting the ions inside in order to make the device, the implantation of these ions are so systematic, you can see that it leads to completely Gaussian kind of distribution inside the medium. And then you realize it when you can just think of what good quality of devices you will be able to do it. Now here I have just given the example how the light is capable of bringing the information of the material, that is optical properties, how the electron bombardment, electronic energy, how the electron beam help us to bring the information about the material, what is the dimension, at what dimension level you will be able to find out. X-rays will also help us to understand what kind of arrangement of the atoms are inside the material. Heavy ions gives rise to maximum information about the material. So in order to understand the properties of the material, you will be using ion beam. Now these are the stages how the primary electrons or secondary electrons are getting ejected, and how the mixing will be done, and how the quenching will take place. As I mentioned in the second slide, that the property of the material will be very, very good the moment when the material is quenched. So you can see that when the ion beam is moving inside the material, surrounding to that one, that localized temperature reaches of the order of 2000 degrees centigrade. The moment when the ion just passes outside, the material temperature will come equivalent to room temperature, which is not possible from the conventional method. But ion does that one. Suddenly going to the 2000 degrees Kelvin, 2000 Kelvin and suddenly coming to 300 Kelvin. So see what beauty of having the quenching mechanism, which leads to patterning of the material, changing the properties of the material. Well, you can see, enjoy this one. Well, bombarded, and what kind of things has happened? So you can see that all electrons from the inner side has been come outside, whereas the surface of this watermelon remains intact. Somebody has rightly given the answer that it depends on the force, and the impact and what kind of collision will take place. So these are the classical diagram, video clip I thought of just sharing among you. Well, now Rutherford experiment, I don't think that you need a complete explanation about the Rutherford experiment, which shows that there is a discovery of nucleus. Now we are almost more than 100 years, 67 in the sense 2067, closer to 2067, closer to 100 years we are celebrating it. Well, these are the mechanism you are using ion beam in order to understand what type of material properties are there. Well, let me explain this one. Now, having said this one, these are many applications when I am telling it, where do we get this ion? Now, you have freedom to use it. Inter-University Accelerator Center using 15 unit double pelletron accelerator, where you will be able to get huge amount of energy depending on the type of ions you will be using. If you are using a proton beam, you can go maximum of 50 MeV. If you are going for gold beam or silicon beam or any inert gas beam, then depending on that one, you will be getting energetic ion beam. Now, super LINAC, where energy can go in terms of giga electron volt also, that facility is also developed in the IUAC. When you want very low energy, only the surface modification patterning has to be done, then you can use Institute of Physics, which is located at Bhubaneswar. That facility can be used at where 3 megavolt tandem accelerator facilities located. Okay. So another one is IG-CAR Kalpakam. There you will be having 1.7 megavolt tandem accelerator, where you will be able to get ion beam, and according to the requirement, you can just write the proposal, and if the proposal is accepted by the scientific community, you will get good chance to use that facility. IUAC accept 5 types of beam time. Probably you can visit to the IUAC and get the information about what type of proposal has to be sent to those research institutes. Well, this is the nano patterning. As I mentioned, as I promised Galgali sir, that I will be sharing 1 or 2 slides in order to show how the nano patterning will be created. Friends, you see it. This is ion-induced crystallization of hafnium crystal having a thickness of 10 nanometer on the surface on the substrate, and these are the images taken by transmission electron microscope or high resolution TEM. Now you say that before irradiation, you can see that the distribution of the ions of the order of 2.6 nanometer. The moment when it is bombarded with 100 MeV silver, 100 MeV silver is the energy, and this is the type of ion. When it is hit to the surface of the hafnium crystal, hafnium semiconducting material, which is making a lot of a kind of revolutionary in the semiconductor technology. You can see that when it is bombarded with affluence of 3 into 10 to the power 12 ions per centimeter square, there is a modification in the structure or in the size of the particles here, which is coming from 2.6 nanometer to 2.8 nanometer. Further increase, this is further increase going up to 10 to the power 13 fluence. What you are seeing is, again, the particle size is increasing up to 3.6 nanometer. When you're increasing 3 into 10 to the power 13, again it is increasing. So particle size is increasing the moment when you go and see what is happening inside the size. So you can see that this diagram, particular diagram. So no doubt the diagram, the size of the ion, size of the particle is increasing, but between the particles, what is happening? There is an erosion is taking place, and this erosion, what you are seeing is a kind of ripple pattern, is of the order of 0.31 nanometer, which is seen at the orientation of 111 direction. So when you see other direction, in the sense, when you go to the other side, you can see that these ripple pattern are completely uniform in nature. And you can see that the distance between the this erosion part is around 0.28 nanometer. So of this size, you will be able to create the patterning. And these patterning are very, very useful in order to see, say, example, solar energy conversion, light into electricity. And when the light is falling on the surface, maximum amount of light is going outside. But when you are creating this kind of nano patterning on the surface, maximum amount of light will be utilized, and maximum light, in the sense, maximum wavelength of the light or the electromagnetic radiation will be utilized, and it will be converted into electricity. So where the efficiency of the material will be drastically changing by nano patterning on the surface. Well, these are the structure that I just thought of sharing it. This is not my work. This is the work done by Professor SVS Nageshwar Rao at Central University. With his permission, I am just presenting his work. Well, this is coming to my work. Most of my work is modification of ferroelectric polymer using ion beam technology. These are just an experimental setup where our students have used it at IUAC, and this picture video shows that there is a blinking of the light. You can see it. So blinking of the light is there. At the same time, when the ion beam are hitting to the surface, you can see that because of thermal spike model, the surface is getting heated up, and the burning of the material, you can see it. Burning in the sense, a kind of erosion is taking place on the surface. Well, two important experimental experimental proposal has been accepted by Inter-University Accelerator Center, where almost 3 PhD students have completed their work. And what are the important work we have taken it? One is using ion beam. One project is ion beam induced modification of ferroelectric polymer composites for EMI shielding, electromagnetic interference shielding. So being a physics person, I know what are the important mechanism required in order to have proper shielding material. So in a shielding material, I know that the electromagnetic waves, when it is hitting to the surface, either the waves should get reflected back, or the waves may be penetrating inner side. The penetrated waves should get absorbed by the intermediate side. So for what should be there so that the absorption will take place? What should be there when the reflection should be there? The reflection of the waves should happen. So reflection will happen the moment when the surface of this polymer is made up of essentially a conducting material. The absorption or multiple reflection inside the material, which leads to again a type of absorption only. So absorption is a phenomena where two types of absorption will take place. One is direct absorption or multiple absorption. For that one, you need a material which has good dielectric constant, as well as good magnetic material, in the sense this epsilon r and the mu r should be very, very high. Now, when you are having a material whose dielectric constant is more, whose magnetic property is more, magnetic susceptibility is more, and the conducting properties. Suppose if you combined these property in a single material, believe it, achieving shielding efficiency will be very, very excellent. And that is what we have achieved it. We achieved almost 60 decibel shielding efficiency in ion beam treated polymer, ferroelectric polymer. And that, in fact, we have published also. I will be showing it in another. I will be having another half an hour. Hope organizers also seeing the time. I will be having another 29 minutes, right?
Yes, sir, you are right, sir.
Yeah, fine.
Go
Now,
slow,
another proposal what has been accepted by the scientific community is using battery separator, using separators which is made up of PVDF only. That is important ferroelectric polymer material. I am using it for my research. So that ferroelectric polymer in some cases has been used directly as a separator. Now, separator, why we required this separator? Now, you see that when the ions and electrons are moving opposite to each other, the moment when the charging is done, so you will be able to see that the charges will be moving. Positive ion and negative ions are moving, and you will be seeing that the charging will take place. So certain amount of energy will be stored. When it is discharging, what will happen? Because of discharging will take place the moment when the electrons are liberated and make a closed loop in it. So in the process of charging and discharging, I have taken an example of a metal air battery. One side, the anode, the one electrode is made up of a zinc and another electrode is made up of air. In the sense, you have a foam where the oxygen will be going inner side is considered to be another anode. Oxygen will help us to make a means make a reaction with electrolyte and liberate the electrons. So you need to liberate the electrons by the reaction. I'm not going deeper into the chemistry part of it. But at the same time, what happens in the sense, now zinc, when you're charging it, the zincs will be liberated. Sorry, when you're discharging it, the zinc will be liberated. When you're charging it, the zinc need to go back and get deposited on the surface. Now, what is happening here is the basic problem is that when you're charging, whatever the zinc has come into this liquid called as a zincate, and because of application of the electric field, which is required for charging, the zincate should go and get deposited on the plate. But what happens? The zincate which is going and sitting on the plate will get pile up on each other. One zincate goes and other second zincate goes and sits there. Another zincate goes and sits there. In this way, zinc atoms are considered to be very, very hard. This is what most important thing that you need to remember. Now, when a large in a localized way in a smaller region, when large amount of zinc goes and sits back on the surface, a kind of layer will be created, which is in the form of thrones only, are called as dendrites. Now these dendrites are so these dendrites are so dangerous the moment when it grows up inside the medium. So this dendrites moves from this layer to it moves to the other side. So there will be always a short circuit, and because of this short circuit, people are not able to use it. Now, people what they thought it. Now, if you want to protect from this short circuit, one can put a layer between these two, where that this layer can sustain for longer duration. At least the life of the battery can be increased. But the moment when the layer is put up, when a proper layer as a separator is put up, so you won't find out much movement of the ions. So obviously, drastically, the power of the battery will reduces. So what our team has thought of, you put a layer between these electrodes, but those layers you treat it with ion beam so that you can create complete systematic porosity into the material, and that porosity, from the porosity, you can see that there is a movement of the charge particles. So this is the idea. So here I used a PVDF film and completely irradiated with ion beam. Irradiation has been done. But whereas in case of EMI shielding, what we did is we did implantation. Ion beam should go and sit inside. It should create a porosity and then it should go and sit inner side. And we have used different type of ion, which creates large number of means it increases the dielectric constant or it increases the conductivity of the material. So to increase the conductivity material, we took carbon beam. We saw that the conductivity has been increased. And in order to increase the dielectric constant, we used oxygen beam. So appropriate type of oxygen beam, appropriate type of energy, and appropriate type of fluence has been used in order to modify the polymer material for EMI shielding and the polymer material as a separator in battery. So these are the two important results I just thought of explaining it. I don't need away from where the electromagnetic radiations are coming and how the electromagnetic radiations are useful for our daily life. So SBS3, what I mentioned it, the information what you are going to send it to the satellite and the information what you are going to get it from the satellite to the earth is essentially using a carrier is electromagnetic radiation of range Ku band. And I was just reading it, how this SBS3 is working. Fortunately, I got to know that they're using Ku band, and fortunately, our group has did a lot of experiment using Ku band only. Okay, so these X band as well as Ku band has been opted in order to understand how the EMI shielding effectiveness can be increased in different type of materials. So I will be. This is what the electromagnetic interference. So people can ask how you are going to get this interference. Nowadays, you're seeing we all depends on the technology. In the sense, we all depends on electronic gadgets, and each electronic gadgets will be working on the field, electric field, and there is always a mismatching of the electromagnetic field, and interference will take place, and lot of distortion of this information will take place, or at the same time, one can see that these electromagnetic interference may create an hazardous to the human body also. So that is the reason one has to create a shielding material which can shield this electromagnetic interference, and all kind of problems can be restored, or all kind of not restoring, all problems can be constrained on it. Okay, shielding has to be used. Okay, these are the mechanism. I don't have to go deeper. These are the mathematical equation. If somebody really interested, I can share the mathematical equation later also. I am interested only in the case of result. Now you see that there are conventional method where you are able to shield the electromagnetic interference just by using a metal shield. You can make a metal cap on the electronic components. When you are having metal cap with a larger thickness, obviously it will take more space. Or you treat with some novel technology using ion beam technology, where you don't require any kind of metal component, metal sheet on it. So by the material itself will become a good shielder. Okay. Well, these are the samples that we used it, and we got whatever the things I have shown it by red color. Now you see that PVDF mixed with carbon nanotube. This is multi-wall carbon nanotube with different concentration, 1 weight percent, 2 weight percent, and 4 weight percent. What we got is, when we mixed with 1 weight percent, this is without what you call ion beam. We modified the properties of the material just by mixing conventional method. And when it 1 weight percent mixed, we got 16.3 decibel EMIAC. When 2 weight percent, 33. When 4 weight percent, 36, which means that as a function of concentration, the shielding effectiveness is increasing. In the same way, here also we got it, but since I have not put it as a red mark, because these values are comparatively lesser than this one. Now you see here 38. When I mixed with 3.15 percentage, and the thickness, what I made is, you got it 38%. And only one group, which is mentioned in this figure, they achieved highest level of shielding effectiveness, that is 56, when they mixed multiple type of nanotubes, multiple type of nanoparticles in the PVDF, that is graphene, nickel, and carbon nanotubes. So tri-type material is mixed with PVDF, and this has been modified, and they got around 56 decibel shielding effectiveness, and they showed that this is the highest value they achieved it compared to what the other material has been used it. Okay, now what is the mechanism here? Mechanism I don't have to repeat once again. When the fast ions are going, you can see that it is creating a thermal spike model, and it will be creating porosity in it. And the pore size is not equivalent throughout the medium. So at the entry level, the porous size will be smaller. At the exit level, the porous size will be longer. So it creates a cone kind of shape. So these cone kind of shapes are very, very favorable for our experimental results. Now, the film, we have taken utmost care to have uniformity on the surface. At the same time, the density of the material is uniform, and this is the technique that has been developed in my lab. Probably I can say that we are able to prepare a thin film of the order of around 250 to 300 micron size, that too self-supporting. Some people say that these are not thin film, these are thick film. Okay, but we can consider anything in terms of micron size can be considered as a thin film, and you can see that how beautifully the films are coming outside. So even the dimension, that area will also be very large. So here in a white color, this is a pure PVDF. I'm showing it. What the picture you are seeing it, clip you are seeing it, is to prepare the thin films of PVDF mixed with carbon nanotube. So that is the reason color is black, and this is white color is a pure PVDF material. So these are the film that we have used it, and we have treated with ion beam. Okay, so this is just to show that we have that facility in us. So these are the different types of beam we have taken. Three beams have been taken: 100 MV oxygen beam, 80 MV carbon beam. In order to have good amount of conductivity in the PVDF material, carbon beam has been used. Good amount of dielectric constant in the PVDF, we have used oxygen beam, and good amount of nickel beam has been used so that we can tune the magnetic properties of the material, and those things has been discussed here. Let us I'm just putting what the values are. Okay, what we observed the moment when the beam is hitting to the surface, suddenly the bulging of the film has been taken place. Now, what kind of bulging has been taken is, now see, pure PVD of, if we use it 250 micron thickness, after bombardment of ion beam, oxygen ion beam of the order of 10 to the power 11, it has gone 310 micron, 250 to 300 micron. So almost it is 20% increase in the thickness has been taken. Later, it has been settled. Continuously, we are bombarding it with a different fluence, higher fluence. So again, it has decreased to 290 micron, and further increase in the fluence, it has settled back to 280, and later it has not changed it. It has not come back to 250. This is just to show that after ion beam implantation, bulging of the film has been taken place. Well, now these are the microstructure, as I mentioned in the title itself, that I'm explaining how the macro patterning will be done and how the nano patterning has been done. Nano patterning already I have shown. Micro patterning. This micro patterning are also called as columnar effect. When the beam is hitting to the surface and going inner side, it is generating a temperature surrounding to that one, and erosion will be taking place, and because of that erosion, you will be able to see that large number of porosity is created. This is the cross-section view of SEM, which clearly shows that how the micro patterning is created inside, which means that porosity has been created. And these porosities are useful when the waves, electromagnetic waves, are going inner side. It has a chances to hit many times to the surface of these columns, and it will reduce its energy, and that is how we will be able to, what do you call, we will be able to get the required result. It is a hypothesis, and similarly we got the result also. And even chemical composition, what happens to the chemical composition the moment when the ion beams are hitting to the surface? Obviously there will be damaging takes place. What kind of damaging will take place? There will be breakage of the bondings between the ions, or there will be free radicals will be generated, and those free radicals will be getting eroded outside because of a gaseous form. It will get exposed, it will get outside, and you will be able to see that erosion will take place, and nice types of what you call columns will be created. And these columns has been shown in picture. Well, this is the setup where we use this setup in order to measure the EMI SE. What happens? One example I will show you. This is the graph which shows when we implanted oxygen ion beam on PVDF. So this black line indicates that when you pure PVDF, what is the EMI SE as a function of frequency? It is almost flat, which is showing of the order of around 15 decibel. The moment when it is implanted with 10 to the power 11 ions per centimeter, red color, you can see that there is sudden increase in the EMI SE. It goes from 15 to 25, and as the frequency increases, somewhere else around 15 gigahertz, the value is very, very large for 10 to the power 11. Whereas 10 to the power 12, it is almost getting flattened and reduced. In the sense, destabilization is taking place at the fluence of 10 to the power 12. Energy is remaining same. But when you go beyond 10 to the power 12, reaches to 10 to the power 13, maximum amount of damages will take place. Free radicals will be taking place, and because of, and it has been predicted, our theory says that in the absorption, multiple reflection is taking place, which is leading to huge amount of EMI SE, which goes almost of the order of 40 decibel at the frequency of 16 to 18 gigahertz. In the same way, for carbon, one problem what we observed is when we are having PVDF with carbon nanotube and bombarded with oxygen, we are getting reduced EMI SE. As predicted, when you are using carbon nanotubes and bombarded with oxygen, this carbon nanotubes suddenly it becomes amorphous. And when it becomes amorphous, it loses its complete characteristics. And that is the reason EMI SE is drastically reduced. So that is what has been shown it here. Then we took PVD of barium titanate, we got quite good results. So where EMI SE has gone of the order of around 50. And when we take PVD of NiO bombarded with oxygen, very beautiful result we got it. We achieved up to 60 in the range, up to 60 decimal in the range of 16 to 17 to 18 gigahertz. So when you are using this PVDF material in electronic components as a shielder, with very less thickness, you can put it on the satellites and send it into this SBS satellites. I am sure that you will be able to protect all the components with this KU band. So this is what the message I thought of just mentioning it. Well, these are complete details that I am showing it. Okay, when oxygen beam with pure PVDF, it gives maximum of 38.89. Carbon nanotube with PVDF unirradiated gives 49.1, but after irradiation, it has drastically reduced. Then these are all reduced when you are taking carbon nanotube. But for the nickel, I think that is missing here. For nickel, somehow that slide is missing. So all this result has been published in a very well-reputed journal, that is Journal of Applied Polymer Science, which is Q1 journal, and Polymer Composite, which is also a Q1 journal. So the result, a remarkable result, what we got it is around 62.80 is the highest one what we received it here. Okay, now the mechanism, we thought of explaining it very quickly. I explain the mechanism and then I will stop it. So our theoretical calculation shows that the EMI shielding effectiveness is contributed to what? So as I mentioned in the previous slide, in the earlier slide, the EMI shielding effectiveness will be taking place because of three mechanisms. One is reflection, second one absorption, and third one is multiple internal reflection, which is again considered as a part of absorption only. So either for proper shielding effectiveness, you need to have good absorption or good reflection. Our theoretical calculation shows what? So this red color indicates the reflection and the green color indicates the total absorption, and this orange color indicates multiple internal reflection, and the faint green indicates the total shielding effectiveness. Now you can see that in all my graph, which has been found out that the multiple internal reflection is taking place. So how we come to the conclusion here? Another important conclusion is that the skin effect. Skin effect means, see, the moment when the electromagnetic waves enter inner side, it loses its energy exponentially downside, is called as 1 by E power. And then 1 by E, what length you are getting it. If the thickness is greater than that one, the skin effect is not going to modify it. You cannot consider that the occurrence of skin effect at all. But our thickness is in terms of micron, and we observed that the skin effect for the combination of ion and the PVDF composites, the skin effect value is very large compared to the thickness of the material. So thickness is lesser than the skin effect. So obviously, when the thickness is lesser than the skin effect, the contribution from the multiple internal reflection will be more dominant, and that is what we observed it. The entire maximum amount of electromagnetic waves will be completely dumping inside the material of thickness 215, similar to black body absorption. Might be, you know that how the black body absorption will take place. Black body absorption, hollow material, inner side, the black material, and multiple reflection will take place. And due to multiple reflection, you will be able to say that the entire waves will be getting deposited inside. Same thing we got it, and that is the reason we reported the main mechanism is due to multiple internal reflection. That is what we have shown it and published in Good News. And second important application is about using the PVDF separator into zinc air battery, and there also we could able to get. Here I thought of just explaining it. Due to shortage of time, I cannot. Okay, porosity, all this mechanism are there. Directly let me go to the result. Well, another important thing, I don't know whether it will work or not. See, a porosity is created. What is the another conventional method to understand the porosity is there? So now when you are having unirradiated film, you can see that the water drop is sitting on side. When you are having irradiated, the water drop is going inner side. This is possible only when the irradiation beam is created a porosity. Now you can see that when I put it a drop on the surface, it goes and sits there. Now this is unirradiated one. This is unirradiated one. Now this second one, the same kind of drop I am putting it on the surface, and you see that what happens to this surface. Now you see that this has stopped on the surface. This is unirradiated surface, and this is irradiated surface. And because of irradiated, the water molecule is going inner side, which eventually tells that yes, the porosity has been created. Now, another way is the moment when you're having porosity, you need to understand that whether this separator is taking the electrolyte out or not. The electrolyte uptake is the another important phenomena to understand the separator is good or not. We saw that yes, the what do you call this electrolyte uptake is also coming in proper order. These are the HSL has been developed in my lab, and using this HSL, we could able to find out the capacitance voltage value in order to understand the charging and discharging of the battery. And we observed that for a longer duration, the charging value is achieved the same value, and discharging value is also achieving the same value. There is no degradation is happening. So that helps us to tell that yes, the dendrite problem, because of uniform distribution of the porosity, has been created. Okay, these are the CV measurements which has been done by Excel, and we used a very low cost experimental setup with very high precision value. That is an XPICE kit, which probably some of people might be knowing about XPICE kit, where using the XPICE kit, we developed our own CV setup. This is the CV setup. Even the cells, all those things has been prepared in my lab only. And you can see that the moment when you put electrolyte and separator in this battery, you are able to see that the voltage is generated, and we light the LED from it. So battery is working perfectly. That is what I showed. Well, these are, you are giving the voltage and how much charging is taking place. That can be understood on the screen. And these are all shown with and without the separator. First one is without the separator, the voltage is going half the way. But the moment when you are using the same separator, unirradiated completely, these are without separator, we are seeing this much of voltage. The moment when you put a separator without irradiation, so sudden increase in the voltage and sudden decrease in the voltage, no passage of the current is taking place, no power is there. So when you irradiate it with 10 to the power 11, you can see that drastic sudden increase in the voltage is taking place, and current is also moving, in the sense there is a movement of the ion is taking place. These are the graphs shown how the voltage variation is taking place. Voltage reduces means it will be utilized to move the ions. That has been observed. Well, this is a zinc air battery without separator. You got this one, and you can see that without separator, you are having power density as well as the current density drawn in this graph. The moment when you put unirradiated separator, there is no current flowing in it, and no kind of what do you call no kind of layer is prepared on the electrode. This is an electrode, zinc electrode. Now you see that this zinc electrode is, you can see that small kind of patch has been created when you're not using an electrode. The moment when a separator, when you're using a separator, no kind of pattern has been created on the surface. It is completely neat, which means that dendrite has not created. So these are the variation of the current density has been shown. A lot of work has been done by my student, and how the variation of the current density has been taken place. Different cycle, first cycle, what is the current density, power density for the zinc air battery, 50th cycle, what is the current density, all those things, 100th cycle, 50th cycle, all different cycles we have seen it, and we saw that the current density and power density has been drastically increased the moment when irradiated PVDF has been utilized. The maximum value that what we achieved is of the order of 59.91 milliwatt per centimeter square has been generated, power generated from our film. And if you are having cascaded a series connected such type of cells, you will be able to create a large amount of power from the battery and can be used it for longer duration. These are CGCD, current charging, what do you call, galvanostatic mode method, where you will be able to see the area is more, in the sense more amount of energy can be stored. That information can be understood from this one. Let us not go deeper into that one. Okay, all these things are again another important experiment where we try to find out what is the electric field generated inside the material due to the passage of charged particle. Okay, so this is electrode free domain rotation from the ion beam, where you can use these techniques in order to rewrite or retrieve the electronic data from the material. A lot of work that I don't want to explain it at this moment of time. So I will skip this one. Summary: the ion matter interaction mechanism for modifying PVDF film is well understood till now, with energetic ion irradiation increasing crystallinity and creating controlled porosity is the new work that we have put it into the scientific community. This modified PVDF based nanocomposite exhibit enhanced EMI-AC. That is what we have shown. Successfully demonstrated in a functional device that zinc air battery with an irradiated PVDF separator showed excellent electrolyte uptake and increased power density. This combination of composites we have taken. We have not purely just taken purely PVDF and studied it. We made composites out of it and then irradiated it or implanted it, where we will be able to find out the synergetic effect of these two mechanisms leading to higher properties that we wanted to require. References: these are the few references that I used it for making the presentation. And at the end, let me just brief about our department. These are the people that we are in the department. One is Professor J.T. Tiperudrappa, who is expert in spectroscopy and a lot of work in spectroscopy as well as interaction of nanomaterials with drug molecules, and they studied optical properties. Another person is Dr. Kotesh MG, who is working on nanoscience and spectroscopy. And the third person is working on environmental radiation and material science using different types of radiation. And me, purely working on ion beam modification and working materials are ferroelectric nanomaterials only. And radiation damage and reliability is the another important part that I am thinking of working. Okay, so these are brief about our department. These are my group: SS Kulkarni, who is presently associate professor at Gupta Institute of Technology, KLS organization only. He is the first student who has completed PhD purely on PVDF work only. And the second person is Bibi Raza Khan. Presently, he is assistant professor at Presidency University, Bangalore. And this person is a Prachalit who has worked a lot on drug molecule and gamma irradiation, and presently at Engineering College at Bangalore. And these are the two people, Mr. Santosh and Mr. Arshad. Santosh is working on EMI-AC, and this Arshad is working on battery application. Praveen, he is from Belgaum. He started working on aerogels. His work has to be accelerated. And this person recently he joined. He is a department first person, and he is working on thermoelectric generators, combining with solar energy and using irradiation technology, ion beam technology, in order to modify the materials. So these are my research group, and I am available here, and I am always available on this mobile phone. So at the end, let me just acknowledge the people who have directly helped me. One is IUAC people, Dr. Praveen Kumar, Dr. Ambuj Tripathi, and Mr. Ramcharan Meena, and entire Peloton group, who have helped me a lot in order to do the experiment at IUAC New Delhi. These are all senior scientists. And the EMI shielding process has been done at University of Hyderabad with the help of James Raju, with the help of SVS Nageshwar Rao and Mr. Arun Kumar. And at the end, I must thank that Dr. V.A. Kulkarni, principal of VDRIT, for having given an opportunity to share some of my experimental results to you people. Hope you enjoyed it. And at the same time, the person behind this entire organizing team is Professor Samir Galgili, coordinator of FDP, ATAL of FDP. I really thank him for giving an opportunity, and at the same time organizing team, because conducting any event cannot be done by single person. You need a team, and whatever team behind this entire organization is there, I really thank them. And at the last, the KLS, Karnataka Law Society management, who is doing wonderful by having two important organizations in the engineering sectors. They are doing well, and I got an opportunity to work them in the earlier days. I could not work at VDRIT Haliyal for some different reason, but I thank them for giving the opportunity during those days also, and now also I thank. If you are having any kind of questions, the session is open. Hope I have taken 4 minutes, 5 minutes extra. For that, I am extremely sorry.
No problem, sir. Not at all. It was a very picturesque presentation, sir. And those picture itself were self-explanation, and your words have added more value to that, sir. Thank you very much. Thank you so much.
Thank you, sir.
Dear participants, if you have any questions, it is open now. Please unmute yourself and ask questions if you have any.
And please switch on the camera also, so that I can
Yes,
see
sir.
who is asking
Yes.
the question.
Yes, sir. Yes, sir.
Yes, any question?
Any questions?
Don't think that asking the question is very difficult job. You can ask any kind of questions. Any kind of questions. Let it be at elementary level, elementary level, any kind of questions you can ask. There is no problem. If I know, I will be able to justify that one. If I don't know, I will say that I don't know. Yes, Manjunath Manipati, please.
No, sir. Thank you.
Yeah, please unmute the mic. I can see you, but your mic is off.
Hello, participants. If you have any questions, go ahead.
Okay, fine. Not an issue, sir. Maybe student people, participants are hesitating to ask the question, but I have given number. Any kind of information you required or any kind of facility at IUAC New Delhi. Since I did my PhD, so with that authority, I can say that IUAC, Inter-University Accelerator Facility, is excellent for accelerator research facility. You can use it for getting that facility. If you need any kind of help, I'm always there.
Sure, sir, sure. And definitely our participants have heard you, and they were very attentive, and some of them were very responding also very quick. And on behalf of all the participants, sir, I wholeheartedly thank you for your exciting presentation. And on behalf of KLS management, on behalf of my beloved principal, Dr. V.A. Kulkarni sir, and on behalf of all my entire team who have done, incredible work in managing this FDP, I wholeheartedly thank you, sir. And I hope in our all future endeavors, you will be there to help us and guide us also.
I will do this.
Yes, sir. Yes, sir. Thank you so much, sir. And our next presenter, Dr. Sridhar Mundinmani, is also here. And Sridhar, sir, are you there?
Good evening, sir. I'm here, sir.
Yes, yes, sir. Sir, please, Uday Kumar, sir, would like to see you.
Yes, sir. Kadke, sir, I know, sir, from Jain College of Engineering, Belgaum, sir.
Yeah.
So when I joined that time, he left actually.
Great. Nice seeing you, sir, on the screen. It's really nice.
Thank you, sir. Thank you very much.
Sir, sir, Uday, sir, thank you so much, sir, from the bottom of my heart. And if you permit, we will go with our next session, sir.
Sure, sir. Sure.
Yes, sir. Thank you, sir. Thank you very much.
I can leave the meeting now. I can leave the meeting.
Yes, sir. Yes, sir. You are, if you permit me, we will share your contact details, sir. Can I? So that participants in future, if they have any questions, they can contact. Yes.
Yes. Not an
Okay.
issue. Huh?
Okay. Thank you, sir. Thank you. Thank you very much. So, dear participants, now our next session is speaker is already there. and it gives me an immense pleasure to introduce Dr. Sridhar Mundinmani sir to all of you. To begin with, he is one of my close friend, and Dr. Sridhar completed his MSc in the area of condensed matter physics in the year 2008 from the Department of Physics, Karnataka University, Dharwad, and he completed his PhD in the year 2016 under the able guidance of Dr. M.K. Rabindranath sir with a thesis titled Nanostructured Materials and Their Composites for Energy Storage Device Applications. Before presently, he is a scientist at Forensic Science Laboratory, Jalhalli, Bengaluru. And before joining Forensic Science Laboratory, he has a 15 years of teaching experience in various reputed colleges. Among them, before he joined FSL, he was assistant professor at Siddhaganga Institute of Technology, Tumkuru. And during his tenure as an assistant professor, I could able to notice that there were a large number of student projects he used to carry out during his tenure, and all were funded. And presently, two students are doing PhD under his guidance, and he has won many awards and recognitions to his credit. I will just read a few of them. The Best Poster Award presentation at National Seminar on Characterization and Processing of Advanced Materials, NSC PAM in the year 2021, held in the Department of Physics, Government Pandit Shamcharan Shukla College in Raipur, Chhattisgarh, and Best Poster Award for his paper Tin Oxide Based Low Voltage Transparent Heater in an international conference on nano engineering science and research advances, and for his project titled Green Synthesis of Metal Oxides and Natural Dye Sensitized Solar Cells. He has received a very good number of recognitions. Among them, the IASC and INSA and NASI Summer Research Fellowship, and the Royal Society of Chemistry, Journal of Materials Chemistry. A best poster presentation is awarded for this particular project, and the best research paper award in the third international conference at NanoCon 14, organized by Bharatiya Vidyapeeth Deemed University, Pune. And he has delivered a great number of invited talks in many of the colleges, and for me it is very exciting to know that if anybody of you can also contact him for a customized low cost scientific instruments, and he and his team has done spray pyrolysis unit. There is a precise laser cutting machines they have invented on their own, and there are smart electronic systems for irrigation that waters the plant when the soil moisture is low. Like that, there are a large number of projects, and to his credit, there are 20 research articles in reputed journals, and he has also authored one chapter in a book titled Supercapacitors and Their Applications, and has filed 4 patents to his credits, and has a reviewer for almost more than 15 to 16 journals. And if I keep on listing, it is never ending. And Dr. Sridhar sir, thank you so much for being with us. And in today's talk, definitely people, as you have already shared your presentation, nano fabrication techniques, fantastic. And thank you very much for joining with us. And I hope on behalf of all my colleagues here, I wholeheartedly welcome you. And over to you, sir. Sridhar sir.
Good evening, everyone.
It's sir, it is already 7:48 now. You have a
Yes, sir.
time 9 o'clock, sir, and I'm very sure you will.
No, like I have exactly 1 hour or 1 hour 20 minutes, sir.
1 hour 15 minutes, sir. You can.
Okay. Okay,
Okay.
no problem, sir. No problem.
Okay. Okay.
Yeah. Thank you. Thank you very much, sir. Shall I start the session?
Yes, sir. You can start, sir.
Okay. Hi, everyone. Good evening. Myself, Dr. Sridhar, and I'm working as a scientific officer in now Forensic Science Laboratory. Earlier, I was assistant professor at Department of Physics, Siddhartha Institute of Technology. Today, my topic is on nanofabrication techniques. Particularly, I wanted to talk on molecular beam epitaxy, chemical vapor deposition, and atomic layer deposition. So, before going to nanofabrications, I will start with the basics. So outline is like this. So first we need to understand the physics, and later electronics. Later we need electronic devices, and later we will discuss nanofabrications in particular techniques. In that there are several techniques to create or to have these nano devices. In that, I'm particularly discussing three of the main industrial nanofabrication techniques. So one is molecular beam epitaxy and chemical vapor deposition and atomic layer deposition. So I will start with the physics. So we already know that physics is the study of matter, and it is it is a study of matter. 1 minute. Yeah, and its fundamental constituents, its motion and behavior through space and time, and it's also the study of energy and force. So why, if we know the physics, then only we can have the electronics. Electronics is nothing but the study of flow of electrons, and it's the branch of physics which deals with electrical engineering, that deals with the emission, behavior, and effects of electrons and with electronic devices. So after having electronics, we need to understand electronic devices. Electronic devices are the devices which usually, operates below the 15 voltage. Okay. So these are all the electronic devices. Here, I'm showing you the few images that we have transistors, resistors, capacitors, and diodes, and these are all independent electronic components. Similarly, we have integrated circuits. So these are all integrated circuits. In that, we will be having too many resistors, too many transistors, and it's a complex circuit. Nowadays, what we are using in our computers, motherboards, and in our digital cameras, in our cell phones, all are integrated circuits. So some examples actually includes a motherboard with a semiconductor material or a microchip. Actually, whenever we open our computer, we will be having a microprocessor, and also we will be having random access memories. All these electronic devices like smart gadgets, what we have, all these consist electronic devices. We also classify these electronic devices as active component and a passive component. Those electronic devices which use power, we call it as a active component, and those electronic components which does not use power supplies like resistor and all, we call it as a passive uh, components. So here are the few electronic gadgets. Now you can see here smartphone, tablets, laptop, desktop, gaming console, gaming control. All these electronic gadgets, they need micro electronic devices or microchips or integrated circuits. So for this, for all these things, all these electronic gadgets in 1990s, we will not be having, CRTs like cathode ray tubes. We were not having smart devices like your mobile phone or your laptop, flexible electronics and all. Earlier days, we were having cathode ray tubes, which were bulky and not flexible and not flexible at all. So in recent days, as the technology developed, we were having microprocessors and integrated circuits. So because of all these the improvements of or the enhancement in the electronic industry, so that is why we were able to concise the size of these electronic gadgets to our fingertip now. Okay, so that is why this the advancement of electronic gadgets which are based on the microchips or integrated circuits. So again, these integrated circuits or electronic devices are completely based on the fabrication technology. We already know that Moore's law. There is one law, Moore's. Then now, as the year goes on, we can put so many transistors in one electronic chip. Okay, so here now it's almost saturated. By 2025. Approximately 3 trillion transistors are included in 1 centimeter by 1 centimeter semiconductor chip. So that is why, as the you know transistors are included in this small chip, so the advancement and the processing speed is very high, and we are having super fast electronic gadgets in our hand. Why I'm discussing these things? It's all because of these gadgets are very much essential nowadays. You can take GPS, or you can take recent advancements like in wireless transfer of your data like Bluetooth, or you can take share my data, everything, all which requires these processors and microchips and integrated circuits. These are prepared using semiconductors, and these processors, microchips, ICs cannot be prepared using metals or insulators. For these processors or microchips or integrated circuits, we are completely dependent on semiconductors. In particular, all the researchers are behind silicon and germanium whenever we have these electronic gadgets. So see here, semiconductor manufacturing process. So if I want to consider these, I want to prepare these electronic devices, I should have a silicon with me, pure silicon or pure germanium. So for that, for industry purpose, I need to have these silicon wafers. See here, you can see wafer preparation in the top left corner. These ingot, it is prepared using chemical preparation, and once this ingot is prepared, and we will take a slice, and one ingot costing us somewhere around 1 crore at present day, and one slice, pure silicon slice, is costing us somewhere around 30,000 or 40,000. In this, we will be using 1 centimeter to prepare one microprocessor of i5 processor, or our A3 processor of Apple iPhone. So in this particular disk, 10 centimeter diameter disk, I will be having approximately some 10 or 20 devices of laptop or computers. So the preparation of this wafer is again a huge technology, and very limited countries are producing these silicon wafers. And similarly with the germanium, or INSE or INP, whatever. All these semiconductors are really used in preparation of microprocessors. In this presentation, I'm going to concentrate on only silicon devices or germanium devices. So these are we are using in present day electronic devices. Once we have these silicon wafers, we are going to create the patterns using lithography technology. There are again so many methods. Lithography, we have molecular beam, ion beam, and chemical vapor deposition, and we have several patterns like atomic layer deposition. So we have all these methods to prepare the patterns on these silicon wafers. Why we need to have silicon wafer, and why we need to have pattern on these wafers? It is because to have 3 trillion or 2 trillion or 1 trillion transistors on this 1 centimeter by 1 centimeter chip. I will show you those things. Here, in the third session, you can see once lithographically, we will etch where all the devices are required. So later, what we will do, we will dope with, we already know that semiconductors are classified in terms of, intrinsic and extrinsic. So to create this intrinsic, extrinsic, P type and N type, we need to dope these pure silicon. Then only we will be having, transistors in our silicon chip. So for that, we will be using, different type of materials. You can see here, this is the P substrate, and we will be having a N type of material here so that it can act as a junction. So once we have junction, so later we can take contact on these silicon wafer, and we can have devices, minute devices. Present day technology shows that one, in even our Apple processors, Apple, they say that 3 nanometer is the lowest they can etch or they can create. 3 nanometer is the transistor size, or 3 nanometer is the one electronic component size in this particular wafer. So now we will come to this fourth part, that is a physical vapor deposition. Using this physical vapor deposition, we can deposit different type of metals, semiconductors onto the substrate of this silicon. Okay, so once we deposit, and it is highly controllable. That is what I'm going to discuss in the further part. One is molecular beam epitaxy and chemical vapor deposition, and I will be discussing atomic layer deposition. So, having said that, we need to, being a researcher, we need to have a control on these devices or the fabrication, and these designs or the alignment or arrangement of these transistors or resistors or capacitors in the silicon chip. Again, it is designed by electronic engineering people using the software called VLSI. And those VLSI people, they create, on computer, they create these designs, and later they will put it in this software, and that software will automatically control the deposition and the etching part of this silicon. In the fifth part, you can see here etching. Etching is nothing but the removal of active component or active material from the substrate. Like if I'm taking silicon on this silicon as an active material, if I want to create a well, so I need to etch that particular material so that I can fill that well with some other material, so I can have P type or N type, PN type, or PN junctions I can have. So that is why, see, etching is very important, and that etching is present day. They are, it is happening in the scale of nanometer. Yeah, here in this fifth, in this fifth diagram, if you can see the dimension here, you can see the dimension is approximately 3 nanometer, and it is so complex. Anywhere in the world, quietly few laboratories are preparing this type of etching, and one is actually, it is in Taiwan. We have Taiwan-based company, so that is only manufacturing these electronic chips. Earlier, our Prime Minister was also telling, the fabrication of chip or the creation of these chips has to be done in India. During COVID time, we already know that, mobile phones were costly, laptops were costly. Why? Because the process was stopped. Okay, Taiwan industry, which is supplying these microchips, was completely, it was suffering from this COVID. So they stopped the, process. So that is why we were having shortage of chips. So that is why in India or in US, we were not having, cell phones, and the same cell phone which is selling 10,000 rupees, that in during those COVID days, it was selling at 15,000 rupees, only because of the shortage of these chips. And now we'll see, the important part of this electronic device is not only the creation or to etch the materials, also we need to protect it from the dust. When we compare simple transistor of 3 nanometer, when you compare that 3 nanometer transistor with the simple dust particle, then the dust particle becomes huge in front of that 3 nanometer transistor. So that is why you need to control, you need to protect these silicon chips from the dust, and how you are going to protect it. So for that we have a packaging. Okay, packaging technology is again a huge technology which is again not established completely in India. This is again done in China and Taiwan. Okay, and see what we do actually in this whatever ICs we are seeing here in the part of sixth packaging, only like 2 millimeter by 2 millimeter is the silicon chip size, and remaining all part is completely, it is a black plastic which is having inside gold wires. Again, gold wires are of few micrometer dimension. So once we, for 2 millimeter by 2 millimeter chip, silicon chip, to cover that one, we are using this much plastic just to avoid the dust. And also, once we connect it, and it can liberate heat. So that is why, to avoid that heat, again, few chips are having now, below that we will place some, cooling paste, so that whenever heat is generated, that heat will be absorbed by that particular paste. You might be seeing in our motherboards of computers, there where what we do actually, i5 processor, below i5 processor, on top of i5 processor, what we'll do, we'll paste cooling paste, and later, and on top of that we will be having a cooling fan. Okay, so that will take out the heat material, heat energy, and it will liberate it to the atmosphere. So this is how these electronic devices and semiconductor devices are it became a part of our daily day-to-day life. So till today, till now, I discussed the wafer part, and pattern creation, why these patterns are very much essential. I told you already, this will help us to put so many components in 1 centimeter by 1 centimeter silicon chip. See, here we can see in this third, and we can again these dope these silicon, pure silicon chips. People are using silicon and silicon oxide chips, silicon substrates, to create these pure semiconductor devices. I'm only concentrating on silicon here, and few people, few electronic devices, or few electronic components, they are also using germanium. Just to give an example, thermistors are prepared using germanium, a semiconductor. Okay, doping can be done using different materials. People are using phosphorus, carbon, and graphene. So the different type of material, based on the requirement, they are you're doping with the pure silicon, and they are having these devices. So I already discussed about the semiconductor device manufacturing, which involves a complex series of processes that I already showed you by graphical representation, that transforms actually raw material. Here, if we want to consider, raw material is silicon, okay, or germanium pure wafer, into finished devices. So finished device here in our concept is actually 1 centimeter by 1 centimeter micro processor, okay, or micro chip, okay, which is having approximately, in our example, I'm considering it as a 3 trillion transistors in that 1 centimeter by 1 centimeter. Very recently, Apple 15, which iPhone announced, which is having A15 processor. In that, they are saying that it is the smallest component size is 3 nanometer. In India, very recently, IIT Madras people, they have developed, and the size of the one transistor was approximately somewhere around 30 micrometer. And when you compare that 30 micrometer with this 3 nanometer size, it is a huge gap. Like it is somewhere around 3 lakh difference in 10 to the power of 5 difference is there between our manufactured chip and the Apple A15 processor. So here the process is, we are actually categorizing it by a major 4 stages. One is wafer fabrication. Wafer fabrication is again a huge, technology that we don't have here in India. And this is again, only few countries are manufacturing these wafers. And wafers, if you want to pure wafers, if you want to buy, that's how I told you, silicon wafers of 10 centimeter dia, they're costing us somewhere around 30 to 40,000 rupees. pure silicon only. Later, by taking those silicon wafers, we will etch and we will create some transistors, and later we will use it for our microprocessors. And wafer testing assembly, whether these wafer, whatever created here in this first process, these wafers are having any defects, and are these wafers are defect free, or these are having any bubbles or any air gas or air trap. So those things have to be understood properly, so then only these wafers can be used for the microprocessing or electronic device manufacturing. And I already discussed about this packaging. So only if you prepare electronic devices using out of the silicon or germanium wafers, it is not sufficient. You need to pack that in the insulated environment, so that whatever heat or dust which sits on that processor, it will not affect the transistor which are there inside that particular electronic chip. So finally, once we have packaging, once we did wafer testing, and later we did etching, and we have our device in that 1 centimeter by 1 centimeter silicon chip, and later we will take it to final testing. Okay, and this each stage has its own unique and set of challenges and opportunities. The semiconductor device manufacturing faces several challenges, including, you know, cost and complexity and yield, but also present significant opportunities for the innovation and growth. So the only company till today, which is dominating this microchip fabrication is TSMC, Taiwan Semiconductor manufacturing company. Okay, he was a student of Massachusetts Institute of Technology, USA, and later he moved to Taiwan, and there he established. And they are selling these fabrication instruments for approximately the cost of one instrument is somewhere around 500 CR. Okay, and we say here in India we wanted to establish semiconductor manufacturing units in India. No, it is very, that is why here this particular semiconductor device manufacturing, several challenges. That is in particular, if we want to discuss, it is cost is very high. And even if we have that particular 500 crore instrument, and the repeatability of creating these wafers, or repeatability having putting these 3 trillion devices on that particular 1 centimeter by 1 centimeter is highly complex. And the yield is also like, if you create 10 chips, out of those 10 chips, 1 or 3 chips will be working, and remaining 7 chips will not be working because of these controlled environment. You have to do this in controlled environment, and the dimension is somewhere around 3 nanometer, and see, little bit like my 1 microsecond exposure of any UV radiation here in this preparation, that can yield, that can ruin the entire manufacturing process. So that is why they create these processes, at least these chips, for a minimum 1 month, or they take A15 process that they create. To create A15 processor, they take 1 month. Okay, to have one processor till today's date it is. Next, what are the fabrication techniques for these creating micro and nano roughness, or to create these electronic devices? First one is, actually we are going to, there are so many advanced technologies. Slowly I will discuss about these the available technologies. The lithography is one of the oldest technology. In that we have photolithography, electron beam lithography, and X-ray lithography. Photolithography is nothing but you will be having a active material, then you expose it to UV radiation. That exposure, whatever pattern you will be putting on that exposure, that will photoactive material will react with UV material, and the well will be created. And once you later you metal you deposit a metal, and then you will be having a device using this lithography. I worked on this lithography. Again, minute error will ruin our devices here. And again, lithography, you can go up to, like, you can consider 1 micron Below, if you want to grow, you need to have the advanced instruments. Without advanced instruments, if you want to go just by rough instruments what you have in your laboratory, maximum you can achieve 50 micron gap in on any substrate like silicon or silicon oxide substrate. And next, the method is soft lithography. Here we have replica molding. Replica molding is nothing but I have a 1 trillion transistor on one silicon wafer, that I will copy it and I will paste it on soft lithography, and then easily I can recreate that mold. So again, molding is the good technology here, and to create that mold again we need to have high end instruments. Next, etching is the third method to have this nanofabrication. In that, etching actually can be done using plasma or laser etching, or chemically we can etch substrates, or electrochemically you can etch these substrates. Here, plasma means here we are going to supply high amount of voltage, approximately 800 voltage or 400 voltage, and this is done in controlled atmosphere like argon or neon or nitrogen atmosphere. So then only we can etch the material without any defects. Laser etching also can be done, but laser point itself, it should be less than 1 micron or 10 micron. It depends on the dimension of your laser point. Then using this laser etching, it is difficult to achieve 1 nanometer gap in between the electrodes. And people are now very recently they are creating using laser opto electronics. They are creating they are catching one atom of nitrogen using this laser etching is also highly effective. Based on the requirements, people are adapting these nanofabrication techniques. They based on the requirements. If you the size of the sensor, like if you go to market, if you want to buy Arduino, you take LPG gas sensor. In that Arduino, people will sell that sensor for 200 rupees. Again, in that, if you open that sensor, you will be having again 3 or 4 centimeter sensor. Active material is somewhere around 3 millimeter by 3 millimeter, and 3 millimeter by 3 millimeter, 1 millimeter will be going for contacts, and 1 millimeter is for active material. 1 millimeter, when it compares to 1 nanometer, it's very huge. So that is why 200 nanometer these LPG sensors are sold for 200 rupees. And here, based on the requirements for that LPG sensor, I need not to have plasma or these MB, molecular beam epitaxy, the technique to create that LPG sensor. So usually what we will do to create that LPG sensor, we will go for the regular one, photolithography. So easily I can attain 1 micrometer gap here. So people are using, based on the requirements, people are using these nanofabrication techniques. Electrochemical is also the same. What we do, we take a solution. With that, we dip one substrate here, and later one will be anode, one will be cathode. We'll pass the current so that the substrate will leave its material. So electrochemically etching. So that means it gives it automatically. It's nothing but the creation of well in the active material or active substrate like silicon. And similarly, only taking part in the active material is not sufficient. Later, you need to deposit also. Like I need to have current collectors on that silicon chip. So for that, I need to coat gold or copper or aluminum. So for that, I need to see the which type of deposition are required. Deposition methods also I need to understand. For that, we have sol gel method. Here you can see, and dip coating method, spin coating method, spray coating, self-assembly, anodization, electrochemical evaporation method, and chemical vapor deposition, and plasma CVD, plasma chemical vapor deposition. And sol gel method is a regular method. Easily you can take any two solutions, and easily you can dip and you can create your own element on silicon chip. Dip coating is again, it is a you take silicon chip and dip it in any solvent, you take gold chloride and pass the current, then automatically gold will come and deposit on the silicon. And here dip coating, we are not using any electrical current or magnetic field, nothing. Just you dip it like it's like paint. So dip active material in paint, it just remove it outside, and the paint will be deposited on that active material. So it is a dip coating. No external energy is required for this. Spin coating is a controlled. Again, you have a solution active material, and we have a silicon chip, and you pour that active material and spin it at a high rate, like 4000 RPM. Uniform, film is formed on this silicon chip. Again, you no need to have external energy here, except that motor which rotates this substrate. Spray coating, again, for this spray coating, we need to have a compressor, so that active material can be sprayed on the substrate. Here usually people are spraying active material on heated substrates. So then only what happens, actually at high temperature, whatever sprayed material will react and it will bind to the substrate. So that is why this technology is also highly used in recent days devices. And self assembly is also very innovative method. We have heterojunctions, or especially functionized material. You can take a dodecane long chain molecules, heptane thiol short chain molecule, and those molecules, like long chain carbon molecules, can be, if this is the silicon, then easily I can deposit these molecules on this. Once you just dip it and you take it out, these thiol molecules will sit on this substrate. They try to align by themselves. So that is why this is called as a self assembly. It's like a school assembly. Whenever at 10:30 bell rings, then automatically children, they go and align in a particular column or row. Okay, so this is called self assembly. Similarly, at nanoscale also, these self assembly takes place on the substrate. This also we worked, and we have published on the self assembly of nanostructures, nano clusters at micro scales. Anodization is nothing but you have a gold chloride solution, you have cathode and anode. Once you supply 5 voltage or 10 voltage, or sometimes it is 15 voltage, 60 voltage, 90 voltage. So what happens, whenever electron releases from this cathode, it electron will flow through this active liquid. In that, gold atoms are present. Then what it will do, electron will catch that gold atom, and it will deposit on the anode. That is what anodization is happening in our lithium ion battery. We call it as a intercalation and deintercalation. So electrons will take lithium ions, and whenever in use, lithium ions will go from one end to another end. Whenever you are charging, then those lithium ions will come back to its original position. So this method is called as intercalation and deintercalation. Again, it's the method of it is not a deposition, actually, it is a anodization. Anodization is only for deposition of active material on any substrate. Similarly, we have electrochemical method. Usually earlier days, our vehicles used to have these mudguards of chrome plated. So all these chrome plated mudguards are created using this electrochemical method. So this is not for the nanofabrication. The same technology has been adopted for the chrome is nothing but, again, metal, highly conducting metal, which is going to deposit on the silicon chip. So that is why the larger scale we have mudguard which is coated with the chrome. So that is why in our any vehicle, you can say it is already coated with the chrome. Okay. And evaporation is also you can do, like we were working on like graphene, like graphene oxide activation. That time what we did, we took a TGA solution, TGA solution, and you heat it. The TGA evaporates and it activates the surface of graphene. So earlier it is a graphene oxide is a non-conducting. Once you activate with hydrogen hydrate wafers, then what happens? This particular surface is highly conducting, and here this surface is non-conducting. So that is why this evaporation method is also deposit. This type of deposition is also plays a vital role, and these are all the methods actually based on the requirements people or scientists or researchers they are using. And chemical vapor deposition, out of all these deposition methods, chemical vapor deposition and plasma CVD deposition methods are costly, but they are accurate, and they give precise results, and we can go till up to few, at least 100 nanometer or 200 nanometer. High end instruments can go up to somewhere around 3 nanometer or 4 nanometer. And another few methods are there in the market now, which are electrospinning. Electrospinning is nothing but you take a carbon. Earlier, Alan Winley, he showed actually the spinning of these carbon nanofibers, and later that technology is used. That carbon, the spinning or weaving of these carbon fibers are used in Mars rover. To just to land this rover, they used these carbon fiber balloons, and in that they put this rover, and they landed it on the Mars. So simple electrospinning is nothing but you have a conducting carbon nanotubes where you give some voltage and spin it. Then what happens actually, they form a thread, or they form a sponge like structure. So that sponge can be used in later applications. So it depends again, based on the application, people are creating this electrospinning, or they are using stretching. Okay, sir, am I audible?
Sir, you are very much audible, sir.
Okay, thank you, sir.
Yes, sir. Yes, sir. Audible.
Yes, yeah. Now in material elaboration, so till now I discussed about the physics, electronic devices, and fabrication techniques. And now I will try to give more inputs on these material. Choosing the material is also highly important here. Here you can see in this slide material elaboration and nanofabrication techniques. Whatever we have here, this nano needle, the white line is approximately 1 micrometer in diameter. Here this particular tip is somewhere around 10 nanometer, this needle tip, this one. Okay, why these needles are required? These needles are required, to have our AFM tips, atomic force microscope, or scanning tunneling microscope, to create those tips. And this one needle, they are selling it for somewhere around $50. Okay, so that is what, to create these needles is high, again huge. We need high-end instruments. Like whenever we go in terms of nanometer scale, we need high-end instruments, and this is the simple transistor what we have here. Okay, here this is the transistor. You can see these are all the current collectors, and this is the active area. Here what they did, they etched, and this substrate whatever we see here, this is silicon, and on top of that we are having, they doped with some other material, and the dimension of this device is somewhere around you take two microns or 3 micron, and particularly this active spot is somewhere around 50 nanometer in dimension. To create this 2 nanometer, 10 nanometer or 50 nanometer, we need again sophisticated technology. And here you can see this is a type of transistor. Here transistor will be having current, the uh, emitter, collector, and base. See here you can see, like 1, 2, 3, 4, 5 connections. We call it as a current collectors. And if you consider this as the base, then this will be collector and emitter. So here we have nano rods. You can see one is orange color, green color, and here again orange color, and there is a thin line which is sitting on these three. And what happens actually, which will be which will be acting as a tri transistor or bi transistor or transistor, based on the application people are creating this. And you can see here, this is the silicon wafer, and on top of that silicon wafer we have nano dots here. Okay, so these nanodots will help us in fabrications. Yeah, anywhere, if you have any doubt, you can stop me and you can ask the questions. Next, material elaboration or nanofabrication technique. So why it is so important? As a researcher, we might want to understand and control the properties of matter to develop knowledge, materials, and working principles. Here, what is the meaning of this one is actually we have a silicon. Silicon was there on Earth for several years, like 10,000 years or billion years. Silicon was there. Very recently, we got to know about this silicon or the usage of silicon in these electronic industry, and we are using it for the at the largest extent. Okay, so you need to have the silicon of the purest form, and later you are going to control that surface with some dopants, and then we are going to deposit on active material or highly conducting material. Those are called as the current collectors. And once you deposit, once you have the junction, then you are going to understand by subjecting it to current voltage characteristics or sensing properties or any controlled atmosphere or any radiation atmosphere. So what happens when you do this, then you are going to develop the knowledge. Very recently, I think last 2 3 years back, or if you want to give best example, 2014, Serge Haroche, what he did actually, he trapped one atom in between this laser light. So that was the understanding of this laser light. So then only they got to know that atoms can be trapped in that photo or in that energy of light. Okay, so this type of advancement will help us to know the matter very much. So for that work, Serge Haroche actually he received Nobel Prize, and it is nothing but the Bose-Einstein condensation. Okay, and few materials also now in market we have more markets. Earlier, the industry was completely dominated by silicon and germanium. Now we have INSE. Like if you want to have mm, white light, white LEDs, and pure blue was challenging in LEDs. So in Japan, very recently, again in 2016, they created perfect blue LEDs, and for that work, they choose active material, different active material, and that work again has been awarded a Nobel Prize. And so what happens actually in this nanofabrication, as you go on diving in this fabrication techniques on material exploration, so you will end up with extremely good results, and those good results are contributing for the society. Okay, so ultimately material scientists are working on materials and changing the properties of that active material. So here, by doing these things, they are doing experimentally, like practical and error methods are giving huge, advantages. And similarly, we have in 2000, I guess, and 2009, Giant GMR, Giant magnetoresistance, that was, invented, and for that, for that work also Nobel Prize has been shared. Okay, so that is why theory and modeling for magnetism or any electronic devices is very important. Simply I have a silicon, I have a device like CVD or PVD. If I deposit any polymer on that one and I have a contact, so though we can create a device, but ultimately we will end up with repeatable in we will end up with in bad devices. Like repeatability will not be there, because we have not controlled the thickness of silicon, we have not controlled the thickness of active material polymer, and we have not controlled the current collector dimension, like metal what we deposit here. So that is why here modeling has to be done. So for that modeling also we have few softwares. We have COMSOL, we have MATLAB. So are many softwares, and those are all highly paid softwares. And theory also, you can you can use Gaussian, you can use Python, you can use Fortran for all these. MATLAB also you can use to understand the mathematical equations. What happens if I increase the thickness? What happens if I increase the voltage? So everything can be, theory and model. Then only people will go for experiments. Then after doing these things, and technical errors will be there, and after that technical errors, people will end up with good devices. Best examples are in our hand. These hard disks, what we are using in our in our laptops. Hard disk will be having a reader. That head is again a silicon tip. Okay. So here, for having all these things, you need to have state-of-the-art materials and devices. Devices are nothing but here instruments. Okay. So already I told you TSMC is selling one instrument for 500 crore. Anywhere in India, we don't have that particular instrument. People actually, our IIC people wanted to buy that, but we were unable to succeed. Okay. We have HRTEM, high-end resolution tunneling electron microscope, which is costing somewhere around 15 crore, which is the high cost instrument which is sitting in the Indian Institute of Science. Okay, and remaining like we have IITs, we are having TATMs, so which are costing us somewhere around 1 or 2 crores. Okay. So that is why the cost is very important here, and he's the monopoly. TSMC is controlling device manufacturing. Okay, you can take whatever we are doing, like say, even Samsung is taking the credits that we are designing, we are taking. No, everyone needs to go to the TSMC for the fabrication of these processors. Even Apple says A15 is fabricated in our own R&D. No, it is not actually what they do. They design it in California, but they give it in TSMC, and they create that chip and they will sell it to Apple. So that is the technology. Next, and access to challenging characterization methods. Okay, you have the devices, but you need to understand, like, have I created a 1 nanometer, transistor on my chip? So for that, you need to have high-end characterization. Assume that you need to have high-resolution tunneling electron microscope to see, one atomic scale. So material elaboration and nanofabrication techniques, why it is difficult in the present era. So you need to combine all these things. Like here I showed material elaboration, like whether I want to use silicon or germanium or INAC or CDAC or CDS. So choosing the material plays a vital role again in fabrication of any components or any sensors on any devices. And again, nanofabrication, like if I want to have 3 nanometer resistor or transistor on my microchip, so then I need to choose the best fabrication method. I already discussed there are so many fabrication methods. Best is lithography, etching, CVD, physical vapor deposition, chemical vapor deposition. all these all these things are there in this nanofabrication techniques. And characterization. Once we create these nanofabrication, later we need to characterize using different type of like equipments. Best example is we need to understand if we want to understand elemental properties, then we need to go for the XPS and EDAX. And you need to understand elemental again, then you need to go for XRD. If you want to know the surface morphology, then you need to have AFM, scanning electron microscope, and tunneling electron microscope, TEM. If you want to go till deeper, then if you want to see 50 nanometer, 1 nanometer, then you need to have high resolution uh, tunneling electron microscope, HRTEM, we say that. And operating cost itself is so high of these instruments. You need to have liquid nitrogen with you, and high current. Assume that 1 kV for 1 hour running the instrument. And even we saw actually in our Delhi University, if we want to turn on this HRTEM, we need to, go on and turn on the instrument at 8 o'clock, and it is usable at 11 o'clock. 3 hours it used to maintain itself. So that is why these are all the instruments, sophisticated instruments, which are helpful for characterization of our prepared devices. And I already discussed theory and modeling are very much essential. Roughly, as a just try method, it will not work in nanoscales or microscales. So you have to model using few softwares. Then only you can choose the material. Then only you can have the exact desired electronic device in your hand at the end. So now why it is difficult, and what we need to do if we want to learn. Okay. So material sciences will help us to understand the material elaboration. I already told you, whether you want to go for the base, a substrate, a silicon substrate or germanium substrate, it depends on you. Okay. Whether you are creating thermistor or transistor, again, it is based completely on you. So choosing the material, these for this choosing material scientists will help you. And nanofabrications, already we know that many technologies. So these nanotechnology people will help you in nanofabrications. And measurement techniques, like if I have already devices, then you need to, which characterization will help me to understand my device. Okay. So that is why these measurement techniques will help you to understand the whatever sensor or whatever electronic device you created after the theory and modeling. Okay. And here are the best examples. You can see here ferromagnetic nanomaterials, metal, and semiconductor molecular beam epitaxy sputtering. See here, I will show you few, materials. Here, these are the materials. You can see here, these are thin films. These particular set of photos are representing thin films. And this particular white line is of dimension of 2 nanometer. Okay. When this width is 2 nanometer and each dot is of few angstroms. Okay. Here, whatever you are seeing, these white dots or black dots are nothing but the atoms of that substrates or any active material what you are using. Okay. Here it is silicon atoms clearly I can see. And here the alignment, the orientation also, they calculated. This is the Miller indices 001. It is the plane in the crystal structure. Once the atoms are arranged in a periodic manner, we will have, lattice structures. Those lattice structures are understood, well, by these Miller indices. Miller indices, represents the planes of that, material. Okay. 001 is the plane here, 100 is the plane. Okay. And 2. And here also you can see this 2 nanometer width. We have like channel like structures here. Okay. Here dot like structures, here channel like structures. And these channels are recently used in water purification. Okay. One of our colleague, she is there in Manchester, UK. She created nano channels for water purification, and which appeared in the best journal Science. Okay. And here, this type of structure, you might be aware, on solar cells, silicon solar cells, you will be having a well-like structures like this. So these are all the islands which are created on that active material. So what exactly is this one? This yellow color is shows silicon, pure silicon, and dopants are sitting, but dopants are actually created islands on that silicon. Okay. Why these islands are important? So to again to have a distinguished properties by these islands. So these are this type of islands are really useful in solar cells. Okay. You take silicon solar cells, or we have dye sensitized solar cells. Dye sensitized, we have other methods, so that we will not discuss. This is purely nano in scale, so that is why these islands are contributing for the electron transportation. So now we have nanowires. I already discussed, and these carbon nanotubes are used in different applications. Carbon nanotubes are used in different sensors. So creating these type of tubes or wires, again, it's huge. Okay, it's huge technology. We worked, our when we were creating, hydrothermal method, TiO2 used, we wanted to create, and that time, by accidental, we were having, TiO2 nanowires on our substrate, and later that we used it for dye sensitized cells, because these nanowires will give high surface area, because on this you can see the dimension of this black line is of 220 nanometer. Okay, 20 nanometer means it's a mini forest on that 2 centimeter by 2 centimeter silicon chip. So this can enhance the specific area. Specific area contributes for specific capacity or specific energy density. In case of supercapacitor, or in case of battery, this one will help us to get the high advanced energy. Okay. Similarly, you can see here, this is also a type of nanowire. This is a nano rod. You can see again, this is 5 nanometer, and here also, we have a plane of this structure, nano cluster. So nano cluster, you can see here, this is the nano cluster is nothing but the arrangement of atoms. Okay, in a particular area. Okay, so this width of this cluster is somewhere around 4 nanometer. Here you can see the representation is like this. This is south and north. This is highly magnetic in nature. And this is the image of this cluster. Okay. And here they are calculating the planes. Okay. And here you can see the device structure. This is of 500 nanometer white line. And this active material here, you can see this is the active material, which is of approximately somewhere around 100 nanometer or 50 nanometer. It is creating this. Here also you can see the Q, this particular area is approximately 100 nanometer, and this width is 35 nanometer here. So for achieving the lowest you achieve, the best devices you are having, and similar in meantime we will be having defects. When you create 10 devices, only 3 devices will be working. Next, the outline. Now, slowly I'm switching it to these chemical vapor deposition and molecular beam epitaxy and ALDs. So, outline of the coming presentation is like material growth and fabrication, some metrological tools, some examples of combination of top-down and bottom-up fabrications. Part one, in that I will discuss material elaboration, actually the thin films and novel materials. And we use a different type of alloys, the combination of two or more metals or semiconductors. We call it as alloys heterostructures. Heterostructures is nothing but layer by layer structures deposited by physical or chemical methods, like physical, I already told you, physical deposition or chemical vapor deposition. Again, based on the requirement, people are choosing the deposition methods. And here we can use these deposition methods can be used to deposit dopants as well as metals. Metals to create current collectors, and dopants can help us to deposit will help us to create these junctions, p-type and n-type, to create these junctions. Once we have these junctions, then only we will be having transistors. Material evaporation or sputtering, molecular beam epitaxy, sputtering deposition, ultra high vacuum evaporation chambers. For this, I'm talking material evaporation or sputtering. We need molecular beam epitaxy or electron beam sputtering. Ultra high vacuum chamber, we need pulse laser deposition. Also, we can do using for this sputtering. Sputtering is used mainly for metal deposition, chemical decomposition or electrolytic growth. So here we have a few methods. One is chemical vapor deposition and atomic layer deposition. This is also highly cost. The size of this instrument is of 10 feet by 10 feet room size of the size of this instrument. Electron beam induced deposition, EBID, and electroplating. Electroplating, I already told you earlier days, vehicles were plated with chrome, so those are all electroplated plates. Similarly, the same technology it is used to deposit the same metals are depositing on 2 mm by 2 mm silicon chips. Okay. If you have any doubt, please stop me. Material elaboration, again, in the same category. Here I'm discussing thin films on a flat substrate. The thickness of those thin films approximately few angstroms to 100 nanometer. Okay, this is the smallest and this is the highest, or this is the biggest and this is the smallest. And amorphous, polycrystalline, epitaxial, flat surface, very low roughness to do heterostructures, control the thickness at the angstrom scale, avoid interdiffusion, sharp interfaces, moderate temperatures. Here is gallium nitride. Again, it is a known semiconductor, gallium nitride, and aluminum indium gallium nitride. This material. Here also you can see the width of this black line is somewhere around 1 nanometer, and you can clearly see gallium nitride atoms here. Okay, gallium nitride. Okay, the same. This is the SAED pattern of this. Uh, okay, this particular image, SAED image of this TEM. Okay. So it is very difficult to create the periodic arrangement to prepare the periodically arranged atoms. Okay, sometimes what happens, the defect formation will be more. So as you control the atmosphere, so the defects will go down. So as you decreases the defects, then only you can use these materials in any applications like sensor or creating any PN junctions or any like solar cells and all. Okay, whatever we see in our solar cell, whatever in market we have, they will be having too many defects. But this is the large scale solar cells what we are using. That particular defect will not contribute for the total outcome of the solar cell. Suppose if it is giving you 1 kilowatt in one day, and small defect will not reduce the power, okay, generation. But when you see, 1 centimeter by 1 centimeter device, and small defect will, cause devastating. It gives very bad results. Properties, perpendicular anisotropy, magnetic coupling, size effect, and electrical properties we can understand from this two-dimensional EG material, metals to insulating materials. So these, yeah, in heterogenic magnetoresistance, for this world only they got the Nobel Prize. And control of interfaces, surface properties, various crystallographic phases, and state of material matter like 2D, 1D, 3D. So all these things are there. 2D materials, we already in recent, 2004, they created this material called graphene. And for this material, for the innovation of this material, for the invention of this material, they got the Nobel Prize, which is called as the highly conducting material, 2D material. Yes. Now I'm switching it to physical vapor deposition. Sir, how many minutes I have now? Hello.
Hello.
Sir, how many minutes I have?
Sir, you have 10 minutes to go, sir.
Okay, then I will quickly finish these things.
Yes,
Now, particularly, I'm concentrating on physical vapor deposition. In the, the task has been assigned for me to, only concentrate on these methods. One is molecular beam epitaxy, chemical vapor deposition, and atomic layer deposition. I have 10 minutes, so I will not waste my time. So, physical vapor deposition, just I will, schematically, I will explain. Here I'm supplying the voltage, and here is the filament. So what happens? Filament will heat the material. So what happens actually? This is in a controlled atmosphere. Assume that it is happening in argon atmosphere. I have aluminum or SNS flakes or whatever. You chrome also you can deposit, copper also you can deposit. So once you heat this material, what happens actually? This metal will melt. Okay, approximately, these aluminum or copper will melt at 400, 500 degrees Celsius in inert atmosphere, and argon gas or neon gas, it will carry those metal and it will deposit on this substrate here. Substrate is nothing but silicon chip, And here this active material is SNS. You can see here SNS flakes. You heat it, and this this will convert it as a vapor, and this vapor will deposit on the active material. So to have the uniform thickness around this silicon wafer, I will be rotating this substrate holder with a motor. So you will be rotating, and uniformly it will be depositing. Everywhere you measure the thickness of this SNS film will be same. Okay, that is the intention. So, and again, these things has to be controlled and done in controlled atmosphere. That is, preferably people are doing this in argon atmosphere, or in vacuum. Okay, 10 raised to minus 6 bar. This is the physical vapor deposition. I wanted to play this, but I'm unable to play this. Here, you can see this is the plasma created, and active material is melting, and it is depositing on this one. Assume you consider this as the active, like if I want to deposit on a mudguard. So this is the mudguard, and I'm depositing here by creating a plasma. How it is done? You can see here nitrogen gas is coming out and going out, yeah, coming in and going out. And here you can see I'm applying the voltage, and this is the substrate. Plasma is created. What this violet color is plasma, and argon is taking this Ti, and it is depositing on this substrate. Okay, and this is possible only when you give bias. Bias is nothing but power supply. Whenever you give power supply, then only these titanium atoms will deposit on this substrate. Okay, so this is the physical vapor deposition. Physical, why physical? Because you are taking active material, and you are supplying power supply, and you are making it to evaporate. So here also, this is here electron beam is also is used, and in this process we used potential. Okay, and here we are using electron beam to vaporize these active material. You can you can deposit all these active material, whatever I'm showing. Here you can consider lead, or you can consider tin, or SN, and gold, copper, aluminum. All these materials can be deposited on the silicon chip or any active material. Okay, and this technique is called as electron gun deposition. What happens actually, this is the gun source, and that gun source is controlled. Electron beam is controlled, and it is made to hit this gold pellets. And once electron beam hits this gold pellets, then gold will melt, and gold atoms will come out. The vapors of this metal will come out, and they hit this substrate, and the uniform layer of this gold or copper or aluminum will be formed on this substrate. Okay, and similarly, joule heating also can be done. Here we are supplying voltage, and if I place copper here, if you apply somewhere around 200 voltage, then what happens? This aluminum will melt, and it will deposit on the substrate whatever you keep. Okay, and this has to be done in vacuum. Okay, nuts and cells is again different type of method, different type to deposit metals on your substrate. Okay, so again, this is usually these evaporation takes place at higher temperature, higher voltages, and higher pressures. You can see vacuum of 10 raised to minus 5 Pascal, and ultra high vacuum is nothing but 10 raised to minus 8 Pascal. And attaining this 10 raised to minus 8 is engineeringly it is very difficult. You need to control the atmosphere, you need to control the instrument, you need to clean every time. So sometimes, attaining 10 raised to minus 3 is also very difficult in India, and people are talking of 10 raised to minus 8 ultra high vacuum. What to create this ultra high vacuum, we have specifically designed the pumps. One is like you can see here, rotary pump. It will take us to 1 Pascal, and turbo pumps will help us to take me to 10 raised to minus 5. Cryogenic pumps or ionic pumps will help me to go for 10 raised to minus 6 or 10 raised to minus 8. Okay, and where we use these things, this is the turbo engine. Okay, to suck the entire gas which is present in the active material. So this type of pumps are used, and these are again only this turbo pumps is costing us somewhere around 3 lakhs, and cryogenic, whenever you go for cryogenic, it crosses 50 lakhs. Okay. So, okay, based on the requirements people are using, cryo and ion pumps are used in very limited institutions like Indian Institute of Sciences or Indian Institute of Technologies. Up to rotary and turbo, we can have it in our in Karnataka, any universities, just to have 10 to minus 5 Pascal. So growth, I will not go in detail of these things. Still, I have not come to this molecular beam epitaxy, but I will give you, okay, what happens actually when we heat the material, these atoms or the energy of atom or electrons will be moving, and they will be, taking the other atoms, so forming islands. What made to form these islands is nothing but the energy of this particular whatever material which is depositing on this one. This is the vapor. Like assume that gold I'm depositing, gold will come and sit, and since this substrate is heated now, so that is why energy will take these atoms together and forms island like structure, and it will not allow to sit these atoms on layer by layer. First the first layer will form. I will show you here. So one layer is formed here. You can see here I'm depositing. The gold atoms are coming, and it is just the same. Even if it falls here, it will because of this temperature, this atom is pulled here, and it is going to form a thin, one layer of gold. Okay. If you want to have second layer, then the evaporation rate should be increased, and that is why we are saying control is very important in these fabrication methods. Either you want to have one layer, now in recent date, theoretically and modeling, people are studying this single layer and bi-layer active materials, okay, tri-layer or multi-layer, this layers. This particular layer, if I consider graphene, so graphene, the arrangement of carbon atoms in a one layer is single layer, and multi-layer graphene is also being used, and it is based on the application, people are using graphene in multi-layer or single layer. Now, molecular beam epitaxy, here you can see this is also a complex system where you need reflection, high energy, electron diffraction, scanning, tunneling microscope, auger, and XPS. Deposition rate is zero point 0.1 angstrom per second. Okay. And vacuum is 10 to minus 9 Pascal. Ion pump, nitrogen trap, and even oven is of 1000 degrees Celsius. Basic research on materials because of multiple possibilities, co-deposition, in situ annealing, controlled by RHEED, 1 to 2 deposit per day, surface preparation, analysis, sample production. And this is the molecular beam epitaxy instrument which is available at CEA INAC France. It looks very easy. If one thing goes wrong here, either this sensor or this pressure gauge, any one thing, if it goes, then the entire instrument should be dismantled and again rearranged. So every time we do this, whenever you run for a go for a new active material deposition. And in this area, this is the molecular beam epitaxy, this is the power supply, and this is the evaporation chamber. Suppose if we want to deposit gold on silicon, so here you have to keep gold, and this is the e-gun. E-gun will help, electron gun will help, to hit the to melt the gold which is there in the evaporation chamber. And this is the electron diffraction, high-end reflection beam introduction chamber. So whenever you want gold, you can open the gate. Whenever you don't want to deposit the gold, you can easily close the gate. So that also you can do here. Ion pump that I told, this will help me to go for 10 raised to minus 9 Pascal. Okay, ion pump. Okay, turbo will help me to go for 10 raised to minus 5 Pascal. And these are, we are having, I think, one ISC professor having this molecular beam epitaxy, but currently, I don't think so it is working in condition. Okay. Uh, Next is sputtering deposition. This is also a type of deposition, sputtering. Usually, again, one fellow who came from US after completing his PhD, who opened one company, Hind Hivac, in Dabaspet in Bangalore. So he started to manufacturing these sputtering machines. He's selling at a very low cost, somewhere around 17 lakhs. These are the lowest. Actually, if you want to go for the foreign instruments, they are costing us somewhere around crores. Okay, so he understood what I need to do for these depositions and all. So he invented. He only manufactured his pumps, and he only manufacturing turbo pumps. So he is creating and using that particular Hind Ivac sputtering instrument. We are able to deposit copper or gold or aluminum, even platinum. Sometimes we use it on our devices for gas sensors or any supercapacitors. So within 2 hours we will deposit, because the pressure, the pressure in 10 raised to minus 5 Pascal easily within 1 hour will attain using these devices. Sputtering is one of the best technology. And even if you have a non-conducting substrates, if you want to go for scanning electron microscope understanding characterization, you need to deposit conducting material on that surface. So before putting it in this SEM instrument, they will sputter some conducting material like gold or copper. They will deposit, they will sputter, and later they will keep it in a scanning electron microscope. Usually, people sputter gold only because it is non-reactive in nature. If you deposit copper, what happens immediately? It turns as a copper oxide. So that is why people will not go for. But if it is single layer, mono layer, or multi-layer, copper is okay. But when it comes to bulk copper, then easily it gets oxidized, by reacting with the oxygen. Okay, and here you can see sputtering rate and ion beam. Usually, if you want to deposit Ag is nothing but silver. So you need to have at 200 electron volt, we will be having 1,000 layers. And similarly, you can see it for different materials, different energy is required. See, these are all the things, and based on this, the whatever manufacturing people, they will ask you like what material you want to use. If I say only gold and copper, then only these the power supplies they will keep, and they will send it to the instrument. If you want all these things, then what they will do, the cost will be automatically increased because of the power supply. Okay, it is again completely required on based on the user application. Yeah, this is the heterostructures I just now I mentioned. Actually, these are the heterostructures, like layer by layer you are going to deposit. Assume that here this is the tantalum and this is the platinum of 200 nanometer. If this instead of 20 nanometer, if this thickness is increased to 21 nanometer, the entire device property is going to change. Okay. So controlled deposition and controlled nanofabrication technique is highly important in this semiconductor fabrication. I already told you they are going to deposit as a dopants. I told you they are here. You can see platinum, bar, magnesium, cobalt, or Fe, ruthenium. See, all these materials are used to create magnetic tunnel junction with active material. This is the tunnel barrier, magnesium oxide. Okay, so this appeared in Canon Abuleva, and this is what the ion beam laboratory looks. Again, this is in France. Japan it was. Okay. Pulsed laser deposition, PLD, is again the instrument looks like this. So instead of electron beam, I'm using a laser beam to evaporate this active material. So once this material evaporates, it will come and sit on this substrate. So I will be having controlled, see, you can see this uniform size of these dots. These dots are nothing but the, like platinum dots of size, 50 micrometer. Okay. This is pulsed laser deposition. Now I have a chemical vapor deposition. Chemical vapor deposition, this is the instrument, chemical vapor deposition. See, the size is room size. And many different types: low pressure, metal oxide, plasma enhanced, and like silicon, and 3,4 gallium nitride, or INSB, these 3, 4 periodic table metal elements. Lower vacuum, higher deposition rates, and very good quality. Chemical vapor deposition gives the best deposition. That is why it is more usefully in industry. Okay. And species introduced in the chamber decompose and react on the substrate. Assume that if I want to deposit graphene growth on copper, see here, this is the graphene which is deposited on copper. Okay. So what they do actually, you know, they give a high energy and plasma will be created and the carbon active material will be there, and carbon material will come, it will evaporate and it will deposit on the substrate, whatever substrate. Like you here, here they are considered copper. We can consider PET sheet also, and silicon chip also we can consider, germanium substrates also I can consider. It is based on the requirement. Okay. Growth rate, you can control this growth also. See here, it is a single layer. If you increase the time, then it will go for the double layer. If you go for 1 day or 2 day deposition, then it will go for a 50 layer or 60 layer. Based on the layers, people are using, graphene in different applications. Atomic layer deposition, you can see high K materials, and but also metals barriers. You can see here these materials evaporates and comes and sits here, and another material will come and sit and forms Al2O3. On substrate, Al2O3 is sitting on this material. Atomic layer deposition it is. Here you can see electrode deposition into nanoporous media. So people are creating these nanopores to have a specific area, high specific area. That specific area will enhance the energy density or any capacity or high sensing rate when you create any sensor out of these materials. Okay. And these type of like porous or nanorods can be created using electrode deposition. I already discussed this. I don't want to go in detail. Still, I have many slides. Nanofabrications, we already discussed top up and bottom up. And top down is nothing but here we are going, from the top, we are going to take out the material. So already material is there. If I take if I dig in that one, then it is a top up. Or bottom up means like you have a precursors, then you are going to create a bulk material, then that is a bottom up approach. See here in top down, I eliminated and I created well, okay, in on any substrate. So that is why it is based on the requirement people are using. You can see here this channel, this device, the dimension of this device is somewhere around 20 nanometer. You can see here 20 nanometer. They created source, drain. This is nothing but collector, emitter and base. Okay. Source, drain and gate. Okay. And they have a PN junction here. This is the transistor, CMOS transistor downscaling. Okay, I will not go in detail. And yeah, I want to show you these images. Whatever processor we are using in our i5 processor or i3 processors, you can see here these are layered microprocessors. In that one layer, two layer, three layer, 100 layers, 1,000 layer will be there, and each layer is contributing transistors. You can see here this is the transistor in CPU nowadays. People say that this is the quad core or dual core. So the dual core is nothing but you will be having two cores in that processor, and each core is of these layers. Okay. And processor graphics, graphic card is inbuilt nowadays in processors. And to control these cores and graphic card, we will be having a system agent memory. This is not a RAM, but a system agent memory. But in phones and all, we will be having a memory chip aside and storage chip one side. Okay, these are completely separated. And nowadays in your cell phone, there are people are saying 4+4 GB RAM. Why? Because whenever you need extra RAM, then this particular area is also contributing for this random access memory. So that means this is 4 GB RAM. Whenever you want 8 GB, then you have the option in software. So you are going to access this particular unaccessed area. So this is what the Moore's law, as I already told you. In 1991, in 1971, I can place only 2,300 transistor in one chip. Okay, transistor count it is. But in 2008, it already went, you can see here, it is 10 crore, transistors in this 2008. And the dimension also you can see here, this is 32 nanometer and highly precise, high yield, high output and low cost, very, good devices. You can see now these are the heterostructures based on the applications. Yeah, why I wanted to show you this one. This is the hard disk and this is the tip. You can see here, this is the tips, TMR it is. And this tip is consisting of all these materials. And to create this material, it's again a huge challenge. 25 nanometer width. And in this 25 nanometers, all these materials are deposited using the well-known technology. Okay, so I will not go in detail. And yeah, clean room is very much essential to have uh, for this. 1 minute. Clean room technology is very much essential to fabricate these devices because this is all controlled because one dust molecule in front of 1 nanometer transistor is very huge. So for that you need to have high-end clean rooms. So, in Karnataka, I think two or three academical research laboratories are having clean rooms. Industrially, Samsung and with Tejas Networks, a few companies they are having in their R&D. Okay, clean rooms are must. Without a clean room, you cannot create these devices. Molecular beam epitaxy. Now, I came to the main topic, molecular beam epitaxy. Here we are using electron gun for the evaporation. So everywhere the concept is same. I will be having the active material. Active material is this one. Here you can see this is the gold, and here is the electron gun. Electron will come, electron beam will come and hit this gold or platinum, and it will evaporate. And this is the substrate. Okay, here substrate is rotating, so that is why the formation, uniform formation of films is possible. Okay, this is molecular beam epitaxy. And this is also done in a high-end, ultra-high vacuum or else a controlled atmosphere argon. Okay, this is chemical vapor deposition. What they do, they will be having a precursor already. You can see here. This is substrate. Okay, you can see here silicon oxide is the substrate, and here tungsten oxide is the precursor. And sulfur or selenium vapor they pass, and it reacts with this one, and molybdenum source metal will be there, and both all these materials will react and they form MOS2 on this silicon oxide or silicon substrate. You can see here the formation mosaic MOS2. Mosaic means like tile structure, tile-like structures here, MOS2, MOS2, MOS2 on this substrate. Uh, yeah, not only you can deposit MOS2, you can deposit any other compositions like people are using gallium nitride, or people are using indium selenium INSE or INSB, based on like LEDs are manufactured using the MBE or CBD. And this is also done in controlled atmosphere. You can see atmospheric pressure, plasma enhanced metal organic frameworks and all, everything metal organic frameworks also you can deposit on that. Key applications of this CVD, semiconductor manufacturing, usually you can see here, this is essential. 1 minute, I have. Yeah, you can see here essential for depositing insulating layers like silicon dioxide or silicon nitride, conductive layers like tungsten, titanium nitride, Ag, copper, or gold, and protective coatings like if you don't want to react that active material with any other things, then wear resistor coatings like paint, what we do on our metal surfaces to avoid rust. Okay, and the diamond like carbon they deposit to avoid the formation of defects. Optics also people are using like for the creating or the coatings, like now whatever I am wearing, this is having a UV reflector, so for this coating also we can use CVD. and mirrors displays offering properties like anti-reflection, anti-glare, specific light reflection. Nanotechnology, it is used to synthesize nanomaterial, carbon nanotubes, nanofibers, and large area graphene films. Biomedical, it is used in coatings on surgical instruments or implants. Okay, advantages and disadvantages on this CVD. We have again too many advantages, and it gives highly pure, dense, uniform fields, but other it works on high temperature, which limits types of compatible survey, hazardous, toxic, inflammable precursor gases that require. These are the disadvantages. And it needs a huge power. Okay. Now, atomic layer deposition, as I already discussed, atomic layer deposition is which is again a sophisticated instrument which I saw and I worked on this MOIST deposition using this ALD in Indian JNCSR. There, Professor Sienna Rao was having this instrument, which is very old, like 10-year old. Now, recent advanced, instruments are available, but right now we don't have that technology in India. But whatever we were having, we used that one to create, layers of molybdenum, molysulfide, or titanium planes like INSB for LED applications we wanted to study. Again, here in this ALD is also, I will show you. This is, I will not go in detail. Yeah, ANS, ZNS films are also can be used. ALD cycle for AL2O3. Based on the application, yeah, ALD process and techniques. What here, aluminum oxide I'm depositing on the substrate. Example, silicon. You can see here, these are the precursors. Here you can see trimethyl aluminum and methyl group and hydroxyl group. What happens next? They will react and they will come and sit on this silicon oxide. It is actually Si and O2. So oxygen will be there. Oxygen will be attracted by this aluminum, and Al2O3 will be formed on this silicon. You can see this is the chemical reaction. You can see here is the reaction. AlClC, CSiO2, and finally we will be having SiAl2O3. Yeah. And here the extra material will be taken out. Okay. Here this material wanted to sit on this, but there is no oxygen to hold this extra molecule. So that is why single layer of Al2O3 deposition is possible on this surface using this ALD process. This is the step 3, and now step 2A. You can see here the deposition is continuous. If you want to have two layer, that is also that can also be done. But whenever we have silicon, only single layer of Al2O3 is required to have the best devices in our hand. Okay. So see now they deposited tri layer. It is a single layer, dual layer, and a tri layer. They'll do. It's all a different time duration, different type of processors, and after 3 cycles, you repeat the cycles, you will be having layers. And for depositing this one layer, it takes somewhere around 1 day for uniform one layer. How you are going to measure this? Then those things, dynamic XPS is possible. So whenever you have aluminum deposition on the substrate, XPS will tell how many layers are deposited on your substrate. And that dynamic XPS is also, I think in India we have only in IISc. Apart from that, we have in Hong Kong or Thailand dynamic XPS. Like during the synthesis process or fabrication process only, you can do it. ALD process and equipment. See now here, we have different types of methods, but the deposition rates and step coverage, you can see the best one is ALD, okay, atomic layer deposition. But for industrial application, having this instrument with well maintenance is useful, or else just a simple error will leads to disaster here. Okay. And ALD process equipments, closed system chambers, so open system chambers, semi-closed chambers, semi-open system chambers. Okay, again, based on the four main types of reactors, I will not go in detail. This is the basic type of ALD. The simple process it looks here, but the size of the instrument is somewhere around 10 feet by 10 feet, you can see here. Okay. ALD process equipments, I will not go in detail. Semi DRAM, memory creates, yeah. This can be used to prepare the semiconductor memory chips, copper interconnect barrier, deposition of porous structures. These can be used. You can see now this is the deposition. Yes, gate, silicon oxide, silicon substrates. These are all Al2O3, HFO2, zirconium oxide. Okay, all these can be used to deposit. For that, we have different precursors. And here again, the same, ALD is the best method to have this one. Again, this ALD is also having advantages and disadvantages. Advantages, we can control the thickness, precisely we can have the material without any defects. Disadvantages, deposition rate slower than CVD. That's what I told you. For single layer deposition, Al2O3, I need 1 day, okay, on silicon chip. Number of different materials that can be deposited is fair compared to molecular beam epitaxy. Okay. So summary here, yeah, advantages and disadvantages. Finally, I thank the management of VDRIT Haliyal, Dr. Samir Galgali, professor at VDRIT. Yeah, he offered me this, talk, and he told me to give the presentation on CVD, MBA, and ALD. I was having, experience on the CVD and MBE and ALD. So that is why, I agreed, and I'm grateful to him. And finally, he remembered and he called me and he followed up. I was not having sufficient time to prepare all these slides, and even I didn't explain my work here. So finally, I thank, ATAL FDP program. And I thank you everyone for listening, 1.5 hour lecture without any break. Thank you. If you have any questions, you can ask.
Sir, very fantastic presentation, sir.
Thank you,
There
sir.
were
Thank you very
two
much.
questions posted in the chat box.
Okay.
The first one is use of nano devices in forensic sciences. By Rajesh Singh, sir is asking use of
Okay.
nano devices in forensic science.
Sir, okay. Nano devices, when it comes, like I just wanted to give one rough example. Suppose, in forensically, if I want to detect cocaine, okay, recent days, USA is selling one a device which it's like a pregnancy kit of 10 centimeter by 2 centimeter. They are selling it for one device is costing us somewhere around $300. Okay, that is being used in all the airports now, present day. Okay, and this nanotechnology helped our own Indian people, like National Forensic Science University, which is there in Gandhinagar. One madam, she created the same device at 50 rupees. $300, which means 3,000 rupees. Okay, no, yeah, approximately 3,000 rupees, and the cost has been completely reduced using this nanofabrication. She used some active materials, and she able to detect cocaine using these nano devices. And when you come to our cyber division or digital forensics, whatever we are having our computers, those are having high-end graphic cards, high-end processors, and high-end memory. Now, whatever cyber digital forensics people we are using, we are having the maximum RAM of 256 GB. And the size of 256 GB is RAM size I'm telling, approximately 4 centimeter by 10 centimeter. 256 GB RAM. And whatever laptop I'm using here, this is of 8 GB RAM, and the size of this one is 4 centimeter by 5 centimeter. So double of this centimeter, I will be having 256. So these nano devices, of course, the end result, high-end technology, which is used in forensic science, and the lower end common people are using. You take my processor is i5. This is the third generation processor, which is having 8 GB RAM. So it doesn't require that much capacity. Okay. But whereas in forensically, I need to experiment with the good things. So that is why I need to have high-end specification. There, these nano devices are coming into picture, sir.
Sir, and the second question is
Yes, sir.
how to improve adhesion across the surface of substrate?
Sir, for that, as per my understanding, I'm going to answer for this question. Even we were facing some problems, whenever we deposit copper on this PET sheet, copper used to peel off. Okay.
Yes.
And later,
Yep.
what we tried, actually, we deposited aluminum on top of copper, and again it came off. So the problem for that one was when we use gloves will be having some chemical, and PET sheet, we used to touch these PET sheets by these gloves, and that chemical, which repels these copper atoms. So that is why what I suggest is here proper cleaning of substrate. Like whenever you are using silicon oxide, usually direct silicon will not come. Actually, silicon oxide wafers will come in market. So that oxide layer, if you want to eliminate, then what people do, they dip it in HF. Okay. And they eliminate that oxide, and purest form they use a metal forcep or a tweezer, and they just rinse it in all the chemicals, and just they keep it in the deposition chamber. But in our case, what we did, we touched with our hands, like by wearing gloves. So that is the problem actually. Cleaning or keeping clean of your substrate is playing very important role. After cleaning also, if the material is not depositing on substrate, means there is something problem in your machine. Example might be with your vacuum or some like inert atmosphere. Assume that if it is not completely 10 it is not, the instrument is not going for 10 to minus 6 Pascal or 10 to minus 2 bar or 3 bar, it is not going. And argon atmosphere is also very important, sir. If you are doing this entire deposition in argon atmosphere, you check the purity of argon. If argon is carrying some other gas, then deposition is not complete. And these things plays a vital role. I'm telling you, in ALD, it is not at all possible. Suppose if I want to have aluminum oxide in silicon substrates, we run actually for 1 month to have one layer on 1 centimeter by 1 centimeter chip. So you should be precise. Tomorrow you have to do again trial and error. Oh, if this is not working, next day I have to try this. Again, you're going to try next day. So finally, we also succeeded. We identified the problem, that the problem is happening. It's because of the gloves chemical. What whenever you remove the gloves, na sir, some kind of powder will come. See, sir, that
Yes.
powder will repel these atoms. That is the problem.
Yes.
I hope I answered this one, sir. I don't
Yes,
know.
definitely, sir. Definitely.
Okay.
Sir, thank you so much. It was a wonderful presentation.
Thank you. Thank you very much, sir.
And as you said, though you were, I must appreciate your skills in understanding the whole subject. And you mentioned that you have worked, and though it is not your, but you quickly came to our help and did deliver just such a fantastic presentation. Thank you
Thank
so
you.
much,
Thank
sir.
you, sir. Thank you very much,
Thank
sir.
you so much.
I don't
And
know
on
I
behalf
gave
of
my
all the
best or not,
participants,
since I'm not in academics, sir, now.
yes,
So
yes,
that
yes,
that is
true.
quite problematic for me.
You
Even
are
I was
now
not
in a
having.
very completely different field.
Th-
But sir, hats off to you. Really commendable.
Thank you. Thank
Presentation
you very
was
much,
very
sir.
nice. Sir,
Thank you.
on behalf of all the participants, I wholeheartedly thank you. And on behalf of my beloved principal, on behalf of management, KLS, on behalf of all my colleagues who are here working day and night for this FDP, I wholeheartedly thank you, sir, for accepting our invitation and giving a talk. And hope your support will continue in future also.
Thank you,
Uh,
sir. Thank you. Definitely,
your
sir.
Thank you, sir. Thank you so much. Um, and I request all the audience participants to just switch on their video for a minute so that we can take one photograph. Uh, uh, Yes, sir. Thank you very much. Thank you, Rajesh sir.
Thank you, sir.
Thank you, sir.
Shall I close the meeting, sir?
Yes, sir. Yes, sir. You can, sir.
Yes, sir. Thank you, sir.
You can, sir. Thank you, sir. Thank you.